Okay, let's get started. In this lecture, we're going to cover speculation, and our focus will be especially speculation in parallel machines. Parallel machines meaning multi-core, multiprocessor, or multi-threaded machines. This is another fascinating topic that has fascinated many people in the world, and many researchers have done a lot of research on this. And in fact, my PhD thesis was on a topic called run-ahead execution, which is essentially speculation, except it was not on a parallel machine, although it could be adopted to a parallel machine, and other people later adopted to it in a parallel machine, as we will discuss with the concept of dual core execution. But basically, that's the idea that we're going to focus on today, speculation. Oh, looks like we're having trouble. Speculation, basically these are some of the readings that are required. Soy et al., Multiscalar processors, a seminal paper on speculation. We will cover that. Zhao's dual core execution work, we will cover that again. Later on, there are two aspects of speculation. Speculation to improve single-threaded programs and speculation to improve parallel programs. The first two papers cover the aspect of speculation to improve single-threaded programs. How can we basically use speculation to parallelize a single-threaded program? The second two papers cover aspects of using speculation to actually improve the parallel performance, parallel application performance. One is transactional memory, which is actually used in some systems today. And the other is speculative lock elision, basically transactional memory done underneath without support from the programmer, at least without much support from the programmer. And there are a bunch of recommended readings that I have. One is actually Stefan, that should be Stefan et al., a scalable approach to thread level speculation, one of the earlier thread level speculation papers. The other one is dynamic multi-threading processor, Hytham Akre and Driscoll's paper. And there are many, many others that I will talk about during this lecture. That I hope you will read about. So the focus of this lecture is speculation in parallel machines. What is speculation? Speculation is doing something before you know it's needed. This is the most general form of speculation. Basically, before you need something, do it. For example, before you know that you're going to fetch this instruction, fetch it. And you need that to keep the pipeline full, right, in a single-threaded machine. So this is mainly used to enhance performance. In the single processor context, you know of many techniques, and we've studied many techniques previously, especially if you have taken my class 447, Computer Architecture, which is, whose lectures are available online. You can actually go back and look at branch prediction, for example. Branch prediction is a form of speculation in the context of single processor. You fetch the next instruction before you know that you should fetch that instruction, right? That's the idea of branch prediction, to be able to keep the pipeline full. Data value prediction is another concept. When you load a data value, maybe it takes a while to load the data value. Why don't you predict that value so that you can speculatively process the dependent instructions? And this breaks the data dependencies between instructions and enables instruction level parallelism. Of course, you will need to verify the speculation that you did in branch prediction and data value prediction, right? If you mispredicted the branch, when the branch actually resolves, you need to recover from that misprediction, so that by redirecting the fetch to the correct destination or correct target of the branch. Similarly with data value prediction, if you mispredict the data value, all of the dependent instructions may be executed, and you will need to recover from that by actually either re-executing the dependent instructions or flushing the pipeline and restarting, just like you would normally do with a branch prediction. Prefetching is another form of speculation. Basically, the processor requests an address before it knows it really needs that address, right? It could figure out based on the address patterns that are happening so far. For example, if the program is generating addresses that are predictable, then the processor itself can start latching onto that address pattern, the prefetcher. Let's say the program has generated A plus 1, A plus 2 to memory to access. The prefetcher can start saying, oh, I expect the program will continue accessing in the streaming fashion or striding fashion with a stride of 1 cache block. And the prefetcher can start prefetching these blocks, right? And this is a form of speculation because the prefetcher just guesses that the processor will continue accessing memory in the streaming fashion, right? Well, in this case, you don't need to recover from it potentially, right? Because there's no harm done. This is purely speculative. whereas branch prediction normally is not purely, it's a speculation mechanism, but it does affect correctness if you do not correct the outcome of the branch. Okay, so these are some of the techniques we had considered when we covered speculation in single processor context. Today, our context will really be parallel machines or multiprocessors. Basically, what are the speculation techniques to improve performance on a multiprocessor system? If you would like to learn more about the single processor context, I would encourage you to go and watch the branch prediction lecture from 447. I believe it's lecture 10 or 11, and it's on YouTube. And data value prediction and prefetching are also covered in lectures in 447, and you can find those lectures on YouTube as well. Or I'd be happy to discuss that in a recitation. So let's take a look at the multiprocessor context. Multiprocessor context, again, there are many speculation approaches. Thread level speculation, transactional memory, and helper threads, but we're going to examine many others. So basically, the idea is to speculatively parallelize the programs in a multiprocessor to improve performance. To be able to do that, we would like to execute threads unsafely in parallel. Unsafely meaning we do not know whether or not we should be executing threads in parallel, right? That's the idea. Threads can be from a sequential or a parallel application. This is the most general form of speculative parallelization. We want to parallelize either a single thread application, or we want to expose more parallelism from a more parallel application. Well, once you start executing threads in parallel without knowing that they can be executed in parallel, they might actually have data dependencies, right? You need to somehow check for these data dependencies. Let's say you've generated this thread 0, this is a thread that's executing, and you start to speculatively fork thread 1, and you continue executing thread 0. And you do not know whether this thread 1 has a data dependency with thread 0, right? Before you start executing it. But somehow, this thread 1 may write to a location that's later read by this thread 0, which means that they shouldn't be executed in parallel, at least purely. So hardware or software monitors for these data dependence violations, and once it detects that, if there's an ordering, data dependence ordering is violated, then the offending thread is squashed and restarted, right? For example, this thread, this is one form of data dependence speculation, that violation. It may be that this thread does a load, and this thread may be logically earlier in the program, and this thread should have done a store, and this thread did the load earlier, but this thread does the store later. This thread got the wrong data value because it did the load much earlier because it was executed in parallel. If it were not executed in parallel, this load would have been done later than the store. And the hardware or the software somehow detects this, and it detects this data dependence ordering violation. This load must have been done before the store, but because of speculative parallelization of these two threads, this store happens later than this load. As a result, there is an offending thread. Offending thread is thread 1 in this case because it's logically later. It should be logically later, but it got the data value that's stale, that was not updated because it executed too early. So this thread can be squashed and restarted. This is one way of actually monitoring and recovering from data dependence violations. Why? Because this thread's execution was unsafe, right? We started executing this thread earlier than we knew whether or not it had a dependence to this part of the program. Right. If there's no data dependence, if you actually spawn this thread and it turned out that these happen to be totally independent, then the thread commits. So one example over here is like basically, let's say you have a single-threaded program, you're executing it, and you have a function call, right? And you execute that function call. Normally, you would execute in a single processor context. But what you can do is you can actually launch another thread, thread 1, let's say, to execute this function call on a separate processor. And this thread actually continues from the return of the function. And if this function is completely independent of this thread, and there is no data dependence violation detected, then you can commit the results of this thread. Somehow you need to merge the results into the architectural state, but actually you can commit, right? Because there is no dependence. So that speculative parallelization works in that case, right? If you're doing a function, for example, that's for cleanup tasks that the processor actually doesn't need over here with this thread, this could potentially happen. Right? or if you're doing a function whose results will be needed much later in the program, you can execute that function in parallel early on right now with the code that's going on that's not dependent on the function, and then later this function's results will be available to other instructions that need the results, right? So this is one case where speculative parallelization can work, right? For example, if threads, if data dependencies are not violated, then the thread commits, the speculative thread commits. And if threads are from a sequential order originally, that sequential order needs to be preserved. If you're actually taking a single thread and parallelizing it speculatively, the sequential order needs to be preserved such that threads commit one by one in order. And we will see this. Basically, when threads execute speculatively, there needs to be inter-thread value communication, right? Let's say you've decided to launch a thread on a function call over here. Then these threads need to communicate somehow. And this can happen via register or memory. And let me talk about the different types of communication briefly, because this will come up over and over in different kinds of thread level speculation mechanisms. If the threads need to communicate through the registers, basically this needs hardware support between processors, right? Actually, the other one needs hardware support too, but the fundamental difference between register dependencies and memory is dependencies between threads are known by the compiler, right? The compiler, for example, when it's compiled the program, it knows, let's say you have a sequential program initially, and this chunk of the program is writing to register 2. And this chunk of the program, let's say this is a function call. You go to function call. This chunk of the program is reading from register 2, right? And doing something with it. Now, if you execute this function call separately as a separate thread, then this dependence needs to be satisfied, right? This R2 actually is executing on the separate thread over here now, because function is actually executing in parallel with whatever comes after the function, destination of the function, or return point of the function. And while that function is executing, this is reading R2, and this R2 is dependent on the other thread that was executing over here, right? So this can be detected by the compiler. That's the fundamental difference between registers and memory. Register dependencies can be analyzed and detected by the compiler because they're static, right? They're not dynamic. Of course, they're dynamic in the sense that they're dependent on the branches, right? That's one difficulty. But you know at least whether or not you may have a dependence or may not have a dependence. Only the branch determines that dependence. But register addresses are known statically, right? Dependencies are known statically. So this register communication, when it happens between threads, can be initiated by the producer of the register, which is this one, or the consumer of the register, depending on which one executes first, right? The compiler can say, oh, this is dependent. You need to wait for the value of the register. Sorry, I did this wrong. Basically, register 2 is used as a source over here. Basically, the compiler can say, oh, you need to wait for the value of this register. It's coming from somewhere. Or you need to send the data that value of this register because somebody else will need it. Compiler, after analyzing that code, that can put in these hints. And if the consumer executes first, let's say this is the consumer thread, thread 1, and let's call this thread 0. If this one executes first in parallel with the previous thread, let's say, and this might happen if you parallelize aggressively, then the consumer stalls. If the value is not ready in the register, it knows that it needs to wait, but the value is not ready in the register file. And the producer, when it executes, it forwards. So how do you know whether or not the value is ready? Well, basically, you can communicate with the register file, and register file can have ready bits, right? For each register in the register file, you can add a ready bit for that particular thread, right? In the hardware, and the ready bit is set if the value is available. And the ready bit is not set if the value is not available yet. For when this thread starts, if the value of R2 has not been produced, the ready bit for that R2 will be initialized to 0. And only when this producer executes, it can basically set that ready bit to 1. So these ready bits are also called full empty bits. And these are actually needed to do synchronization between threads at a very fine grain. Basically, whether or not the value of a register has been produced yet. And the producer sets the ready bit, consumer basically waits for the ready bit to become 1. This is basically data flow between threads. And full empty bits, one of the early introductions of this was Burton Smith's seminal paper on a pipeline shared resource MIMD computer. And I'd encourage you to read that. That has a good example of the use of full empty bits in the heterogeneous element processor that Burton Smith designed at the time. And this is ICPP 1978. But this is an important construct for communicating registers between threads. You could have full empty bits in memory also, actually. This is an important synchronization construct that enables one thread to produce a register or memory value and another thread to consume it. And this is how you can synchronize it. Basically, this is a synchronization variable. Ready bit is a synchronization variable that can be supported in hardware. And if you're doing thread level speculation, you should actually support this in hardware in registers, right? Okay, so you can read this paper for a good use of full empty bits. If the producer executes first, on the other hand, basically producer simply writes the result and sets the ready bits, and when the consumer actually executes, the consumer reads the value. And the producer can continue after setting the ready bit, of course. And we will see one example of this with the multiscalar processor. Multiscalar processor actually communicates between threads this way. There are full empty bits in the register file, and when a task, as they call it, produces a value that needs to go out to some other processor, and a compiler analyzes the task to know whether or not the value needs to go out to some other processor. Then the task, when it produces the value, it basically sends the value across the register file ring, and another processor that's needing that value captures it in its register file. But we will get to that. I'm getting ahead of myself. But this is another reading that you should definitely do. This is actually a required reading. Multiscalar processors in ISCA 1995 by Sohi et al. ISCA 1995. And this is one of your required readings. This is one of the seminal examples of thread level speculation done in hardware-software cooperative way. Okay, and they communicate registers values between processors this way. Okay, I've already said that this can be implemented with full empty bits in registers. Memory communication, on the other hand, is very different from register communication. The compiler has no idea usually about memory dependence. At least the difficult memory dependencies the compiler doesn't know. Why does the compiler not know? Because the compiler doesn't know the memory address of operations, and not everything is statically analyzable because of this, right? For example, if you use pointers in your program and dynamic memory allocation, you allocate memory to a pointer, and you allocate some other piece of memory to a pointer, and you can assign any value to a pointer, right? As a result, these dependencies are dependent on the dynamic inputs to the program, and how does the program behave based on those dynamic inputs, and the compiler cannot analyze that dynamic execution. As a result, memory communication is usually harder to satisfy between these different threads in speculative parallelization. But if you're speculatively parallelizing the program, you would like to know if there's a store here and if there's a load here, if this store and load actually overlap, right? Because if this load actually overlaps with this store, when you're executing this in parallel with this portion of the program, you would like to know that this load actually gets the correct value, and it actually doesn't get the stale value. And similarly, there may be stores here and loads here, and you need to know if this store A is overlapping with this load B, because it may be that you don't want the store A done before the load B if they're actually overlapping with each other, because this is from a logically later part of the program. Right? So you need to preserve the dependencies, obey the dependencies. In general, in thread level speculation approaches, a thread performs loads speculatively and gets the data from the closest predecessor thread. Right? And it keeps a record that it has read the data. And it keeps this record in the L1 cache or another structure. And we will see some examples of this. On the other hand, stores are also performed speculatively. When a thread does a store, it doesn't wait. when a thread does the load, it doesn't wait normally also, as I said earlier. Basically, when a thread does a store, it may not be the oldest thread in the machine yet, so it buffers the updates while it's speculative, while it's not committed yet. Basically, it places the update in the write buffer or in the L1 cache, and when it does a store, it checks for successor threads for premature reads. So this implies an ordering between the threads, right? You have basically thread 0, thread 1, thread 2, thread 3, thread 4, thread 5. They can all be executing in parallel, but there's an order, which is the sequential order, if you're actually parallelizing a single-threaded program and executing them in parallel. In this case, you're taking these threads that are supposed to be sequentially ordered, or chunks of execution that are supposed to be sequentially ordered, and executing them in parallel, thread 4, thread 5, and looking at, checking if they actually have dependencies on loads and stores, if they actually violate any load-store dependencies. So every thread can do the loads speculatively. For example, assume that the loads are actually independent of any store. That could be one assumption. And keep a record that they've actually read the data. This load, for example, loads from address A and keeps a record that, oh, I read from address A. And this can be done in the L1 cache by setting a bit saying, I read the data, right? Speculatively read. And this thread 0 later on, for example, executes a store to location A. At that point, it buffers the store. And it also checks if there's a successor that has already read location A, right? If a successor did a premature read, well, in this case it did, right? This load A happened before the store A, whereas it shouldn't have happened in that order. It's because these are logically sequential threads. Just because we've executed them unsafely in parallel, this load happened before the store. So we need to detect that dependence when the store actually executes, and that's when the dependence is detected. This store basically somehow figures out that figures out a destination load happened earlier, whereas it shouldn't have happened until the store finished. Right? So if the successor basically did a premature read in this case, so it needs to be squashed. Right? Squashing means the thread needs to be restarted, perhaps, and maybe everything else needs to be restarted because you have now a data value dependence that was wrong, because some other thread may have read some other data value that was produced by this load later on, and it got executed with the wrong data value. Basically, you typically squash the offending thread and all of the successors when you detect such a data dependence violation, when you figure out that this thread speculatively read the wrong value. Well, you could do something smarter, but complexity increases in that case, right? You could actually figure out only those dependent instructions that have gotten the wrong value and execute it, and you could selectively re-execute those instructions that are dependent. Right? Now, this is a tough thing to do. It's very hard to figure out selectively which instructions need to be re-executed. And people have looked at this problem and they found some solutions, but in general, it's a difficult thing to do. Okay, so I've given you a lot of the concepts actually in thread level speculation. Basically, when you take a single threaded program and parallelize it unsafely, you run into these dependence issues. And the key dependence issues are register communication and memory communication, and you need to satisfy those. And memory communication needs to be satisfied dynamically, as I said over here. And this kind of communication can happen over here also, right? It doesn't need to be with the oldest thread. This is in this case the oldest thread and the youngest one over here. But it could happen between thread 3 and thread 4. Thread 3 can be, thread 4 can do a load A, and later thread 3 can do a store to load A, and this needs to be detected, and thread 4 and all successors need to be flushed or squashed. Okay, dependencies and versioning. Only true data dependence violations should really cause a thread squash, right? It makes sense. There are types of dependence violations. Let's say you have, in this case, I denote load A and store A. This is the later thread, let's say. The earlier thread does a load to A, later thread does a store to A. In this case, it's really a name dependence. So the hardware should really be able to handle this. Meaning there is really no dependence here. It's really an anti-dependence. It's not a true dependence, right? Basically, there's no reason for, let's say you have thread 0 and thread 1. This does a load A, and this does a store A. And this does a store earlier than this load. You should definitely ensure that this doesn't get the value coming from this store, right? And you should be able to do that by eliminating the name dependencies. And how do you eliminate the name dependencies? Well, you do a register renaming, right? In this case, these are not registers, so you can do memory renaming. Okay, and we'll see one structure that does memory renaming. Whenever you would like to eliminate not true dependencies, write after write, in this case it's a write after write dependence, right? Or write after read dependencies. Well, in this case, I guess write after read dependence, sorry. You can eliminate this dependence by renaming these locations, because essentially the store is really creating a new value which just happens to be in that location, right? A. You can actually think of the store killing the old value in that location and creating a new value, so there's no dependence really. It's really a name dependence because we didn't have enough memory locations, for example. Or you could actually create a new version of that memory location if needed. Okay, the second one is a write after write dependence. If one thread is doing a store to A and the next thread is actually doing the same store to A, the hardware again should ensure that the stores appear in order. And we've covered this subject earlier, right? If the true dependence happens when the older thread is doing a store to a memory location and when the younger thread is actually reading from that memory location with a load. In this case, if the younger thread actually read earlier than the store happened, then this true dependence needs to be detected and it needs to cause a squash because the thread that's younger read the wrong value. So name dependencies, in general, the first two dependencies can be resolved using versioning, right? Basically, every store to a memory location can create a new version, as I just described earlier, right? Because the store is really using that memory location as an address. It's really creating a new value, right? And once you have different versions, for example, whenever this store writes, it creates version 1, whereas this load is loading from version 0, right? So this load can get the correct value because it's really reading from version 0, right? At the time this thread is executing, you have version 0. When this thread is executing, it creates version 1 of that location. When this next thread is executing, let's say it does a store A, it creates a version 2, right? And this thread actually it creates all the version 1s, this thread creates version 2s. As a result, there's no, the name dependencies can be eliminated. Of course, this requires some hardware cost to tag the memory locations with the different version numbers. And one example of this is described in this paper, Speculative Versioning Cache in HPCA 1998. And I encourage you to read that paper. This is one way of handling name dependencies that are not true dependencies. Okay. The other question when you actually design speculative parallelization concepts is, where do you keep the speculative memory state? And let's take a look at that. Basically, what is speculative memory state? Whenever a thread speculatively does a store instruction, you don't know whether that store instruction should actually be committed to the architectural state, right? Because this thread may not be the oldest thread in the machine yet, in the sequential logical order, right? Which means that somehow you need to buffer that store instruction. Well, there are two approaches to this. Where do you put this store? You can put it in a separate buffer. For example, you can put it in a shared queue, store queue that is shared between threads, right? And the idea is whenever you do a store, you have a buffer, and the thread puts its version number, for example, and thread ID into this buffer, and another thread later on checks this buffer to see if there's a store to get the data from, right? If this thread is the older thread, for example, if there's a younger thread that's executing, let's say it does a load, it basically searches the store buffer to see if there are stores from an older thread to the same location, right? So this is the store buffer approach, separate store buffer approach. Now this is an additional data structure, but this is doable certainly. This is very similar to the address resolution buffer in multiscalar processors that we will cover. Basically, address resolution buffer is a way of ensuring that store load dependencies are satisfied in multiscalar processors. This is also similar to run-ahead cache and run-ahead execution that we have covered in 447. The basic idea over here is in run-ahead execution, you speculatively execute the program, and while you're speculatively executing the program, some store instructions actually write speculatively to memory, you don't want to expose them to the architectural state because remember, run-ahead execution is purely speculative, and the load instructions that happen in run-ahead mode get their data values from, if they're dependent on store instructions that are executed in run-ahead mode, they get their data values from this run-ahead cache. And if you're interested in this more, you can read the run-ahead papers that were assigned or that were discussed earlier. On the other hand, you can not have a separate buffer like this, but you can decide to place the speculative store blocks in the L1 cache. In this case, you can mark, basically, in the tag store, you have one additional bit saying speculative bit, right? Speculatively modified bits. And you will see this example when we talk about thread level speculation. And this speculatively modified bit basically says that this cache block was speculatively written by this thread, and normally this is not visible to the other threads, right? You need to make them non-speculative when the thread commits, and you need to invalidate them when the thread is actually squashed. Now basically what you're doing is you're really putting the store buffer into the cache and integrating with the cache. But you need to ensure that cache still operates correctly. And this modifies the cache, but maybe you don't need an extra store buffer if you actually want to keep the speculative memory state. So there are actually interesting trade-offs related to where to keep the speculative memory state, and I'd encourage you to think about it, especially when we come to multiscalar and different kind of approaches to thread level speculation. Okay, I will now delve into speculation to parallelize single-threaded programs. But before I do so, I will take a quick break, and we will get back to this very soon. Okay, let's continue on where we left off. We're going to talk about speculation to parallelize single-threaded programs. That's part of the speculation lecture. And then we're going to focus on speculation to improve the performance of parallel programs. Now, this is a topic that has fascinated many people, and there are many readings that I can recommend over here. And these are some of the reference readings, and all of them are required. Well, that's a joke. The more you read, the better, of course. It's always good to read and understand the ideas and evaluate the different trade-offs between the ideas. This could give you a lot of good project ideas, and this could actually enable you to do great research as well. So I would actually recommend reading all of these papers, but some of these will be required, as I've already told you earlier, and as we will put up on the website. But I'll try to cover some of these. These are the reference readings over here, but there are many, many other readings that we can talk about. So the basic idea of taking a single threaded program and parallelizing it on multiple hardware contexts is called thread level speculation. This is also called speculative multithreading. And there are many examples of it. One example is dynamic multithreading, which basically I have briefly discussed, and I will give this reference over here. But that's an example of it. Akari and Driscoll wrote a paper in Micro 1998 about a dynamic multithreading processor. This is one example of speculation which we will not cover in detail, but I wrote it over there because it's an interesting approach also. The basic idea is whenever a thread gets to a function call, launch the function call on a separate hardware context. So core 0 executes the regular thread, core 1 executes the function call now, and core 0 doesn't twiddle its thumb at that time. Basically, it continues executing from the return point of the function call. So if you think about code, you have some code here, and you have a call here. Basically, this call takes you to some function block, and this function block gets executed over here, and this the next instruction that comes after the call, let's say it's an add, the next block gets executed on this core 0. Right. This is basically function level speculation. At that function, you start a thread. And if there's another function within here, you start another thread, right? If there's another function, you start another thread on a separate hardware context. So that's how you dynamically multi-thread the program at the function level. Now, what happened, what they did over here was, if some of the values were not available, for example, were predicted to be produced by this function, they basically predicted the values. And actually, they predicted the value of the return value of the function. Return register value, right? because function usually produces a register value that's returned. And if that's the case, then that register value is predicted, and this return point is executed with that predicted value. At the end of this function generates some results, and it also generates the register value. That register value is compared to this predicted value, and the result, if the prediction was correct, then the execution here was correct, right? If assuming that all of the predicted values were correctly predicted, right? All of the values that were produced by the earlier part of the program that must have been executed before the return point were correctly produced. So there needs to be some checking to ensure that that happened, and eventually the results get merged, and you merge the results using something called thread result buffers. And I'm not going to go through that in detail. This is a more complicated part of the mechanism, but that's they were able to parallelize programs at the function level this way. This one example. The other way that this particular paper parallelized the programs was with loop iterations. So if you have a for loop, for example, what you can do is when you get to the beginning of the iteration, you can launch the next iteration in another processor. So basically, you can speculatively say iteration 0 goes here, iteration 1 goes here, core 0, core 1, iteration 2 goes here, core 2, and iteration 3 goes here, core 3. As many cores as you would like. And this is another form of speculative parallelization, right? Basically, you can actually predict the inputs to the iteration potentially also, even if there are dependencies between iterations. And you, of course, need to do everything else I said earlier. You need to ensure that the data dependencies, true data dependencies, are correctly satisfied and the iterations execute correctly. And if there is a dependence violation, iterations are actually, iterations and subsequent iterations that saw the dependence violation are actually squashed. So this is the idea of speculative multithreading, thread-level speculation. And people have especially looked at multithreading when you get to a function call and multithreading when you get to an iteration. Basically, in a loop, you can try to parallelize the different iterations of the loop speculatively. And we will get back to these concepts over and over in this lecture. But the basic idea I've already given you, right? Divide a single instruction stream speculatively into multiple threads at compile time or runtime, right? And the key is speculatively. And you can execute speculative threads in multiple hardware contexts, as I've shown over here. And eventually, you need to merge the results into a single stream. For example, this function call needs to merge its results into the single stream such that the results appear as if you've executed that single instruction stream sequentially, right? That's the key idea. And of course, hardware and software, sometimes cooperatively, need to check if any true dependencies are violated during the speculative execution, and it ensures the sequential semantics. Because remember, we have sequential semantics in the single-threaded program, and we need to ensure that semantics. We're only under the hood parallelizing that single-threaded program by utilizing the multiple hardware contexts that are present in hardware. So one potential way of actually doing this is threads can be assumed to be independent. For example, here, the function call is executing another thread, and the return point of the function is executing another thread. Let's assume that they're independent. You can actually use value and branch prediction to break the dependencies between threads. In this case, the return value of the function can be predicted such that the code after the return point can be executed, assuming that it's independent, right? You don't need to wait for that data value. Waiting for that data value could be another option, but that reduces the parallelism between the threads, right? If it's predictable, it may be much better to predict that value that this thread needs to continue execution. Right? So basically, you can use value prediction to break dependencies between threads, and similarly, you can use branch prediction too. Of course, you need to verify such predictions in the end, because remember, this is a single instruction stream that we're speculatively parallelizing. And you can actually verify these predictions by executing a safe version somehow, right? Maybe you always execute the safe version, and also by checking some invariants, right? And we'll see one of those approaches, and you can think of other approaches. So one of the earlier works in thread-level speculation was actually done here at Carnegie Mellon. This is Greg Stefan's paper, A Scalable Approach to Thread-Level Speculation from Todd Murray's group. And this shows an example over here. Basically, I will go over this example on the slide. This is a hard-to-parallelize loop, if you would like. You have a while loop. Let's assume that this while loop executes many times. Basically, you have two accesses. One access loads from a hash table using one index, and the other access actually writes to this hash table somehow and actually some value that's produced. Now, if you would like to parallelize this program, while loop, as a programmer, you have no idea if one loop iteration, iteration 1, is independent of the other loop iteration, right? It may be such that the first iteration is writing to an index that the next iteration is reading, or first iteration is writing to an index that 25th iteration is reading, right? But you have no idea because these indices are dependent on the data values input to the program, and as a result, as a programmer, it's very difficult to parallelize this program by breaking the loop iterations to be executed as on different cores, different threads, right? So, but using thread level speculation, what might happen is basically the idea is to speculatively execute consecutive iterations in consecutive processors. So processor 1 executes iteration 1 over here, right? This is called epoch 1, let's say. Processor 2 executes epoch 2. This is the second iteration. Processor 3 starts executing epoch 3. Processor 4 starts executing epoch 4, right? And these all execute dynamically in parallel. And basically these dependencies are kept track of, right? For example, processor 1 reads from hash 3, but that's okay. No other processor has written into index 3. Processor 2 reads from 19. Processor 3 reads from 33. Processor 4 reads from 10. So the fourth iteration reads from index value 10. And it turns out the first iteration actually writes to index value 10. So this dependence needs to be detected somehow. So this fourth iteration cannot execute in parallel with the first iteration, really, right? Because there is a dependence over here on the fourth iteration actually should get the correct value, whereas it may execute and get the wrong value. Because here, if you look at this in time, it got the fourth iteration's hash 10 read executed earlier than first iteration's hash 10 store, right? Store to index 10, index 2, which is 10. So in this case, this violation needs to be detected because in the sequential order of execution of this while loop, the first iteration should execute before the fourth iteration. So that's the idea in thread level speculation. How do you actually detect this violation? And the idea is to use the coherence protocol to detect this violation. We'll get back to this. But assume that there is no violation. Assume that dynamically these values turned out such that no thread wrote to an index that a later thread actually read. In that case, all of these threads attempt commit at the end of their iteration. And in this attempt commit function, basically they check if there was a violation. If there is no violation at all, a violation meaning the data value read by this thread was actually written by some other thread, and this thread actually got the wrong value because it executed speculatively earlier, right? If there is no violation, then these threads can commit, right? And this commit needs to be in serial order actually, because you need to preserve the sequential semantics of the program. Remember, this is a serial program again. And these threads actually commit in the serial order. And the thread commits assuming the previous thread has committed and it has no violation, right? Well, if there is a violation that needs to be detected, and that gets detected with the coherence protocol, when this processor actually reads hash 10, it doesn't know someone else has written, but when this processor later writes to this index 10, this memory address with index 10, it basically sends an invalidation request to this processor, and this processor, if it has read, remember the principle, when you do a speculative read, you mark the cache or some location saying that, oh, I've actually speculatively read this value. And if later an invalidation comes from an earlier epoch, earlier processor, epoch is the right thing in this case because processors can execute later iterations also. An earlier epoch actually writes to a location that was speculatively read by a later epoch, and you can determine this through the coherence protocol. The coherence message protocol sends an invalidation message to that address, and this cache receives that invalidation message and checks if that block is actually speculatively read. If the block is actually speculatively read, which is the case in this case, and if you're receiving an invalidation from an earlier epoch, that means that you read a value speculatively earlier than someone else should have written to it. As a result, this is a data dependence violation. You read the wrong value. once you read the wrong value, now you need to squash this thread, this epoch over here. And this shows how that actually happens over here. So I'm going to go over this slide again in this. Basically, this is processor 1 and processor 2. Let's say you have epoch 5 and epoch 6 executing, and epoch 6 is the earlier epoch over here. I'm sorry, epoch 5 is the earlier epoch, and it's earlier in the logical sequential order. Epoch 6 executes speculatively. It basically does a load from this memory location, and once it does the load, it needs to send a read request, and it gets the data cache block in its cache. And there are two values, 2 bits added to each cache block, saying whether or not this cache block is speculatively loaded and whether or not this cache block is speculatively modified, as we've discussed earlier, right? When we talked about stores and loads and memory communication earlier. Basically, when this processor does the load, this speculatively loaded bit is set to 1, right? And it's set to 1, and later, let's say, and this processor continues executing with the value of the load. It gets the value of the load, but it's speculative. It may be not the correct value. And later, this epoch 5 executes on processor 1, and it basically does a store to the same to what happens to be the same location, right? Q and P are the same, basically. But these are pointers, so you do not know the location statically, so you cannot parallelize this program. Basically, this does a store. It changes the value from 1 to 2. In this case, the value was set to 1 over here with the load over here. It changes the value from 1 to 2. It basically sets a speculative modified bit in its cache, but it's not important here. That's for other purposes. And it basically, because it's doing a store, it needs to send an invalidation message, right, to everybody else. Remember, this is a cache coherent shared memory machine. When you're doing a store to a cache, it's an invalidation-based protocol in this case. It basically sends an invalidation message to all of the other processors that have the location, either through a directory protocol or through a Snoopy protocol, right? This invalidation message reaches the L1 cache of this processor, which is executing epoch 6. An invalidation message also contains information about which epoch is invalidating. So it has this epoch 5 tag attached to it. And when the L1 cache gets this message, it checks, oh, this invalidation is coming to a speculatively loaded block, which has this bit set, and it's coming from an earlier epoch, logically earlier epoch than the epoch that I have, which means that I've speculatively loaded potentially the incorrect value, right? And in this case, basically, you detect that this is a violation. Once this invalidation message is received, you know that you've read the wrong value and the violation is detected. So there's a violation signal that's set to true over here. Now at this point you can start squashing everything actually, but in this paper they don't do that. What they do is they wait until this attempt commit time, and this attempt commit time actually checks whether the violation bit is set in the cache, and if that violation bit is set, then it starts the recovery process. But basically it basically squashes this entire epoch over here and squashes all of the other epochs that come after it. So this is how you can use cache coherence to detect a read after write dependence violation through the invalidation messages. Now if this was an update-based protocol, you could do the same thing, right? You could actually be even smarter if this is an update-based protocol. If this is an update-based protocol, this epoch would send a message with an update request to this location with its epoch ID and the data, and you would still know that this is speculatively loaded, and you can actually say if the data value that you loaded doesn't match the data value that's sent, then you've gotten the wrong value, right? Then there's a violation. If the data values actually happen to match, then you've gotten the correct value by chance, potentially. Because there are actually a lot of stores that are silent, right? These are called silent stores. And Kevin Lipak has a paper in Micro 2001 on the silent stores, and I'd encourage you to read that paper. Basically, this means that store is storing the same value to the location, same value as the location had before. So an update-based protocol can have that optimization, and it can check whether the data value has changed or not, instead of checking only whether the address is going to be modified with some value that's not known. Okay? So that's the idea. This is how you can detect conflicts in thread-level speculation by leveraging the underlying coherence protocol. This paper actually presented some results, and I'll briefly go over them. I'll encourage you to read this paper. There are actually some promising results. These are some applications, and this is on a 4-processor single-chip multiprocessor, 4-processor single-core multi-core machine. And you can see the speed-ups. There's the parallel region is over here, and the speed-up that you obtain in the parallel region, this is just the parallel coverage. So if you see that the coverage of the parallel region is not very high, which means that Amdahl's law limits the speed-ups to begin with over here. But these show the results. For example, in some applications, you get significant performance benefit with 4 processors, up to 46% performance benefits, and the performance benefit keeps increasing as you add more processors. And remember, this is purely done with thread-level speculation. This is a single-threaded application, parallelized. On some applications, for example, the JPEG compression, you get less benefit, only 8% on the overall program and 94% on the parallel region. And you can see the speed-up curves as you increase the number of processors over here. This is the single-threaded version, up to 8 processors. And this is the execution time of the region, which is the parallel region of the program that they parallelized in this work. So if you can see that this application actually scales in the parallel region, but there are cases where, for example, here, the performance increases up to 4 threads, but as you go up to 6 threads and 8 threads, performance starts decreasing. Execution time starts increasing. In fact, the execution time with 8 threads is worse than the execution time with 1 thread. Why would this happen? Well, this could happen due to multiple reasons, right? Actually, there are many reasons, but in this case, there are lots of dependencies between threads, so there are lots of squashes. That's one reason. There's a lot of ping-ponging that starts happening because now the data gets distributed across the private cache, and you get a lot of invalidations because of the dependencies. And there's bandwidth contention that also happens. These are basically due to the problems that we've discussed in the bottlenecks in the parallel region, right? And these are actually discussed in the paper. I'd encourage you to read this paper. But thread-level speculation approaches like this are quite promising. The downside, as you can see, the upside is you can get significant speed up in the parallel region. The downside is some speed ups are actually low and the complexity may be high in the system. So I'd encourage you to think about the advantages and disadvantages. Okay, let's move to another seminal paper. This is actually an even earlier paper that discussed thread-level speculation. This is called Multiscalar processors. And the key idea is to exploit implicit thread-level parallelism within a serial program, just like what we've discussed earlier. But the approach is different here. In this case, the compiler divides programs into tasks, and the tasks can be defined unclearly, but we will discuss this. And these tasks are basically the portions of a single-threaded program. If you think of single-threaded program as executing a series of instructions that are dynamic, that are composed of static blocks of instructions, basically tasks are some arbitrary subsetting of those blocks. So let's say this is your program, and these are some blocks of instructions. Your tasks are basically blocks in your program, right? Task 0, task 1, task 2, task 3, task 4. They could be loop iterations. They could be functions, right? But the key thing is this is a sequential execution over here. Okay? And we'll see an example of this. Tasks are scheduled on independent processing resources. Instead of executing them on the same processing resource, thread 0 goes to one processor, thread 1 goes to another, thread 2 goes to another, ... Right? Very, very similar to before. And hardware handles register dependencies between tasks. Because these are coming from the same program, there could be register dependencies. This could be writing to register 2, this could be reading from register 2, right? And there may be many dependencies. Hardware handles this register dependencies, but compiler specifies which registers should be communicated between the tasks because compiler knows that information, right? Remember, register dependencies are known to the compiler. Compiler, when it creates the tasks, it basically says, oh, these are the registers that I need, and these are the registers that I'm actually likely to produce. I can produce. Right? And this information is conveyed to the hardware such that the hardware can communicate between the threads. And we will see an example of this. And memory dependencies are handled through memory speculation. Basically, hardware detects and resolves the misspeculation between the tasks, and through something called an address resolution buffer that we will discuss. So this, I would recommend actually both papers over here, but the required paper is a Sohi paper, Multiscalar processors, that appeared in ISCA 1995. This is an earlier paper, the expandable split window paradigm for expanding exploiting fine-grained parallelism. A lot of the concepts are not mature enough yet, but it was also published in ISCA 1992. And certainly the name multiscalar is more catchy, right? Expandable split window paradigm for exploiting fine-grained parallelism doesn't sound that catchy. But when you say multiscalar, it starts becoming more catchy. Anyway, that's the joke of it. But basically, this figure from the multiscalar paper clearly describes what they're trying to do. If you want to have a single-threaded program, and if you want to execute operations in parallel, you would like to execute instructions one by one and figure out, have a large window or execution, right? To actually improve the performance of the program, right? Out of order improves the performance of the program by looking at a large window of instructions. And we already discussed why that large window is harder to build, right? And that led to the multi-core. Increasing performance by building large instruction windows is difficult. Now, if you have a large window of instructions, and if you want to execute multiple instructions per cycle, one of the limitations is, for example, if you want to execute 100 instructions per cycle, let's say, you want to extract that kind of parallelism from your program. To be able to do that, you need to look beyond many instructions in the instruction stream, and also you need to have a width of 100 instructions per cycle, and also you need to have a register file that can support the execution of 100 instructions per cycle, which means that you need to have 200 ports, right? Assuming each instruction has 2 input values, 2 source registers. So building this multi-port register file is tough, right? And this was one of the reasons for move to multi-core. Remember the Kunli-Olukutun paper in 1996 that discussed a multi-ported register file as a part of the technology push of what makes single-core, single-threaded processors unattractive. A similar reason happens here in 1992. And basically, 200-port register file is not scalable. So why don't we actually, instead of having a huge, large window, why don't we chop up this instruction window and execute the different pieces in parallel in different processors? Processor 0 executes task 0, processor 1 executes task 1, processor 2 executes task 2, and processor 3 executes task 3. Now each processor looks at a smaller window, but you can process the entire window, maybe a similar size window, in parallel. And the added benefit is each processor has a simpler register file, right? Why? Because now in order to get the same bandwidth, let's say you want to do 100 instructions per cycle, I was very aggressive here. Now you can do only 25 instructions per cycle in each of these processors, which means that you only need 80 ports. And of course, if you scale this to reasonable values, if you say, I want to do 16 instructions per cycle total, you need 32 ports here. Building a 32-ported register file is still pretty tough. But if you want to execute 16 instructions, you just need to execute 4 instructions per cycle if you have 4 processors, which means that you need to have only 8 ports per register file. And that's actually much more palatable, right? So that's the idea, basically. Now you have a distributed register file and smaller windows, and you've split the large window into smaller windows, and you're extracting parallelism through the multiple hardware contexts. Right? And you have this distributed register file, but you need to somehow ensure that the communication happens correctly in the register file. And we'll take a look at how multiscalar does that. I've already given you the basic idea. So the key idea, exploit parallelism that is provided by a large instruction window in a sequential instruction stream by chopping up that large instruction window into smaller tasks, smaller windows, and executing tasks on those windows in parallel. This not only improves the parallelism, hopefully, because you don't need to extract it from the sequential instruction stream through out-of-order execution methods that are less scalable, for example, through the reservation stations. Hopefully you can extract parallelism much more easily if you create the tasks nicely and assign them to different processors. And also this hopefully simplifies the hardware because you don't need to build these less scalable structures like large reservation stations, large multi-ported register files, because they are now distributed. Reservation stations are distributed over here. Multi-ported register files are also distributed, and you have fewer ports in each. So that's the benefit. And this is the model of execution. Model of execution is very similar, as I've said here. With the superscalar processor, you have a single centralized window, and you have a single program counter, and this is a dynamic instruction stream. With multiscalar processor, you have multiple distributed windows. You basically have multiple program counters. You have program counter 0, program counter 1, dot, 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 over here. And there's a task selection, task assigner over here that assigns different tasks to different cores. So you need to have that centralized engine that actually assigns which task should go to which core. Okay? So what is a task? We've been talking about task. Basically, a task is a subgraph of the control flow graph. It could be a basic block. It could be multiple basic blocks. It could be a loop body. It could be a function. Basically, it could be a loop iteration, right? Tasks are selected by the compiler and conveyed to the hardware, and tasks are predicted and scheduled by the processor. And tasks may have data and or control dependencies, and they need to be resolved. And this is how a multiscalar processor actually looks like. Basically, it has this task sequencer that sequences through the tasks, figures out the next dynamic task, and assigns it to the next processor that's available. And these processors or tasks are ordered in a logical order, in the sequential order that they were assigned. The head task is the oldest task in the system that's executing on this processor, and tasks are actually ordered in a round-robin fashion. This is the next oldest, and this is the tail task, which is the last task over here. And register files are connected through a ring. Basically, when this task actually produces a data value that may be needed for a later task, it basically sends the data value across this ring, and that the tasks that need that data value basically capture them and place them into the register file. Now this is how the full empty bits, remember the full empty bits in the register file, get set. Basically, an earlier task sends a produced value, and the consumer task captures the consumed value from the ring and basically sets the full bit or ready bit of its register, of the register that it's waiting. And how does it know to wait for the register? Well, the compiler specifies that, oh, this register is actually going to be produced by some other task that's earlier than you, because the compiler can analyze those dependencies, right? Okay, so there are several things that the compiler needs to do in multiscalar. First is task selection. You need to partition the control flow graph of a program into tasks. And there are many things that go into this. We're not going to describe this, but there's a paper by Vijay Kumar et al., Task Selection for Multiscalar Processors, that was written in 2001, I believe. You can take a look at that. Basically, there are several things that you need to do. You want to load balance across different processors, right? If one task has 2 instructions, if another task has 2,000 instructions, that doesn't work. So load balancing is important. Again, we go back to the fundamentals. The fundamentals is you would like to minimize overheads and minimize the bottlenecks. Remember, the bottlenecks in the parallel portion is load imbalance. We'd like to eliminate that when we're doing task selection. The second is we would like to minimize the synchronization overhead, right? Which means that we'd like to minimize inter-task data dependencies. So the compiler can look at the control flow graphs and figure out the data flow graph also. It tries to minimize the task dependencies. And also it can try to minimize control dependencies, right? Basically, if the control is predictable, if the control transfers between the different tasks are predictable, then this task sequencer can do a good job assigning tasks to different processors and predicting the next task, which is good. If there's a hard to predict branch, it's better to embed it into a task, because if there's a hard to predict branch that affects only this task and nothing else, then you don't need to flush all of the other tasks, right? The branch prediction can be handled solely within this task. So it's good to embed these hard to predict branches within the tasks. And that's one of the jobs of the multiscalar compiler. And you can read the paper for more detail on the benefits of this. The second job of the multiscalar compiler is to convey the task and communication information in the executable to the hardware. For this, the compiler has the task headers, and the task headers specify several things. One is, actually, let me start with the second one. One is the program counters of the potential successor tasks, right? You can have potential multiple successor tasks in a control flow graph. Now this is the dynamic stream over here, but in a control flow graph you could actually have many potential successors, and the compiler needs to specify which ones, what are the addresses of those successors, such that the task sequencer can use a prediction mechanism to decide which task to choose next. So let's say this is your task. Now this is your task dependence graph, if you will, or task flow graph. I didn't do this well, but you can imagine there could be many successors, right, to a task, and maybe there's an indirect branch, right? So you have these 3 successors after this task, and these successors need to be communicated in the header for this task, such that the task sequencer predicts which one to go to next, which one to sequence to next. The task header also contains information about the register communication, basically which registers are needed by this task, coming from other tasks, because the compiler partitioned the task, right? Potentially needed. And which registers are actually created by this task. This is 1 bit per register. The needed registers are actually not here, but created registers are here, but there's a need mask also. Basically, this indicates all registers that are possibly modified or created by the task. These are actual live outs of the task. That's the create mask, right? It's basically a one hot bit vector of all of the registers that could potentially be modified. There are live outs. And the purpose of this is when you know that you actually are going to modify a task, when you receive, let's say this is your bit vector for the registers that are created, create mask. Let's say this task is modifying register 0, register 5, and register 10. And this task is executing on a processor with this create mask. If another, remember, register file communicates the values. If the register file receives R1, R0 in this case, from the ring, it says, oh, I'm going to create this R0, so I'm not going to use this. Basically, I'm not going to forward this to the next task. Right. So this ensures that the register values are not forwarded unnecessarily. This also ensures that this task actually, when it generates the value, it forwards it to the appropriate places, to other places that need it. Right. There are also release instructions. The compiler also inserts release instructions, which release a register to be forwarded to a receiving task. Basically, we will talk about release instructions soon. The idea of a release instruction is whenever it's executed, the value it generates is put on this ring. Remember the ring? Let me go quickly to, yeah, there you go. When a processor actually executes an instruction, and it's a release instruction, and it's writing to a register, that register gets put on the ring because it's releasing that register value, or forwarding that register value, and that gets sent to a processor that's later on, and that processor basically captures that value if the value is not already ready in its register file. Basically, if it's waiting for that value. And how does it know it's waiting for that value? The compiler can specify that to the processor. Okay, this is an example multiscalar program. Basically, this is an example code segment over here. What this does is it looks for symbols in a linked list, and if the symbol is not present in the linked list, it adds the symbol. And it does it for a many number of symbols that are specified at this buffer size, right? So this is a hard to parallelize program because what happens is if you break it into iterations, you may get dependencies between different versions, different iterations. So you don't know. It's very hard to analyze statically that there are no dependencies. So Multiscalar can actually parallelize this dynamically. And this is the Multiscalar code. This is the example. This is the header for the task. This is the task itself. It's basically one loop iteration. You can actually study this on your own. And it has a create mask. These are registers that are potentially created or live outs from this particular task. These are the potential targets. It could be alter, which is the alter loop, which you go back to this same iteration. Or it could be the alter fallout, which means that you actually get out of this iteration. Basically, this is the task itself, and that's you could either get out or you could either continue the loop iteration that does the search for the symbol. Basically, the task does the search for the symbol, and these are the instructions that forward their values. Basically, register 20, register 23. Those are produced with these instructions, and they get forwarded to other tasks because other tasks need them, and this also produces a value. Other tasks need the register 4, and register 8 and register 17 happen to be produced, but they're released with a release instruction, and we will see the reason for release instructions soon. Stop it means basically you stop the task when you reach this instruction. And I'd encourage you to read Multiscalar paper to get more details. So how does forwarding registers between tasks happen? Basically, the compiler must identify the last instance of a write of writing to a register within a task. You may be writing to a register many times within a task, but we want to forward the only last value, because remember these tasks are from a sequential order. Basically, opcodes that write a register have an additional forward bit indicating this instance, when it's executed, should immediately forward the result once it's executed to the next processor in sequence. Right? And stop bits indicate the end of a task. And release instructions tells the processing element to forward the register value specifically. Basically, you don't you use it. You can either use the forward bits or the release instructions. And there are different cases. Let's take a look at these cases. Let's take a look at this. Let's say this is the task. I'm not showing the control flow instructions here, but let's say you have a load into R1 and another load into R1 over here. Now the second load's value should be forwarded to the next task, because next task is really sequential. Right? This value is basically consumed within the task, so this value is really dead because it's overwritten over here, regardless of which path you've taken to get to this block. So this load actually is annotated with a forward bit, additional forward bit, indicating that the result of R1 should be forwarded on the ring once this load is executed. In this case, this is a separate case. In this case, the task, depending on the control flow it takes, can produce two different values for R1, right? If the control flow is this way, basically this value of R1 should be forwarded to the next task. If the control flow happens to take go this way, then this value of R1 needs to be forwarded to the next task. In this case, these loads are not marked with the forward bits, but there's an additional release instruction added. Once potential values are produced, then you know which value of R1 is actually needs to be forwarded. Then you can just have a release instruction. The compiler inserts that release instruction such that R1 is just released. And the purpose of the release instruction is basically when the release instruction is executed, that register is sent on the ring to the next processor. That's the idea. And release instruction is needed in this case also, as you can see, because if you go this path, R1 is not overwritten, but an old value of R1 needs to be forwarded. If you go this path, a new value of R1 is produced, and that needs to be forwarded. Okay? So how does task sequencing get achieved? Basically, you have headers contain information about what are the potential successor tasks, and task prediction, the task sequencer, which was here before, needs to do task prediction. And this is analogous to branch prediction, and we've discussed branch prediction in 447. You can take a look at that. The idea is to predict the inter-task control flow. And in this case, for example, tasks are chopped up such that there is only one task following task A. As a result, it's very easy to do this prediction, right? Or in this case, task A has a very iterating loop that iterates many times, and task B is the fallout task. In this case, this could be a highly predictable inter-task branch, right? If you look at this. And the prediction may be basically very similar to branch prediction, right? What is the next task coming? In this case, you have two tasks over here, and you predict whether task A or task C comes after task A, and the predictor can get trained, and it can implicitly predict the branches within a task. Right? So that's the idea. This is very similar to branch prediction, but it needs to be done. And an important issue is, how does the compiler form the task such that this prediction is maximized, right? The prediction accuracy is maximized. Okay. How do you handle inter-task dependencies? There are actually control dependencies and data dependencies across the tasks, because the paths actually come from a single sequential stream. Right? For control dependencies, basically we predict, as we discussed. And within a task, there may be dependencies that are control dependencies. Right? And okay, let me go back to inter-task dependencies. If there's a misprediction in the inter-task, subsequent tasks are flushed. Okay? But if there's a misprediction within the task, it's an inter-task misprediction, and I'll show you one example of it. Actually, in the previous example, I could have shown perhaps. Let's say you have this task, and this task starts out this way. And let's say you have an if statement over here and an else statement over here, right? And that's what this is, right? This is the if part, this is the else part, and then you go back. This is a hammock. If there's a misprediction over here, as long as that misprediction doesn't affect anything else, no other task needs to be flushed, right? This misprediction can be handled internally within the task because it doesn't affect the control flow going down. Now it may affect the data values that are needed by later tasks. But that may be okay. That's dependent, that's handled through a separate mechanism, data dependence mechanism. Okay? So basically, intra-task mispredictions are really handled within the task and they don't get exposed. So it's good to embed hard to predict branches into the tasks. That's another job of the compiler that's doing this kind of, that's helping this kind of parallelization. Right? Data dependencies, on the other hand, if data dependencies are through the register file, then we have mask bits and forwarding, as I discussed. Basically, if a task is waiting for a register, then it stalls until that register is available. Right? This is a full empty bit synchronization in the register file. On the other hand, for memory, we have a separate store buffer. Multiscalar proposed a separate store buffer called address resolution buffer. And the idea is loads are speculative. Loads speculatively load the values. And if they actually violate it, if they actually loaded a value they shouldn't have loaded, the task is squashed. Let's take a look at this address resolution buffer. Remember, we've discussed there are two fundamental ways of actually storing values, detecting store load dependencies. One is through a separate buffer, and one is through the L1 cache. In this case, we're going to do it through a separate buffer. The idea is Multiscalar issues loads to this separate buffer, address resolution buffer, or the data cache at the same time, as soon as the address is computed. Address resolution buffer, ARB, is organized like a cache. It maintains state for all outstanding load and store addresses. And you can read this paper for a detailed discussion. An address resolution buffer entry looks like this. Basically, for each stage, it basically takes an address, its address indexed, and for each stage, if you will, stage meaning different processor, it has an entry for that address. And this may not be the best way of doing it, but you get the idea, I think. This is basically a version of that particular location. And this version says, did this stage or did this processor perform a load to this address? And did it perform a store and the data value? And for each stage, you have that speculatively loaded and speculatively stored bits, basically. Right? These are bits that are speculatively loaded and speculatively stored. You could put this in the cache, but they decided to put it in a separate buffer. And this separate buffer actually affects scalability. Basically, when you do loads, let's say you miss in the ARB, address resolution buffer. When any processor does a load, if it misses in the ARB, data comes from the data cache, because you have not seen any prior stores yet. And if there's an ARB hit, the processor gets the most recent data to the load, which may be from the data cache or nearest prior task with speculative bits set to 1. So if you go back to this, the load can get the data value from the nearest prior task, right? So when you do a load, what happens is the processor checks basically the processor checks all of the previous stages. Let's say stage 2 is doing a load. It basically checks all of the prior logical stages. In this case, let's say head is the stage 0. It checks stage 0 and stage 1 also to see if there's actually a store coming from those stages. If there's a store coming from both stages, then the stage 2 gets its data from here, because this is the latest version of the data, if you will. Right? That's the idea. The load gets the latest version from this address resolution buffer, nearest prior task with speculatively stored bit 1. On the other hand, stores, and if the load instruction loads the data later in some way, it sets its load bits as 1 over here, such that if a later task comes and stores, it can detect that violation, right? Okay. Stores, ARB buffers speculative stores. If there's a store from an older task, when it does a store, it basically searches the entry of the ARB, because this is the same block, same cache block. It basically searches to find any later tasks that may potentially have loaded this value, right? So for example, let's say stage 0 does a store to a location. It basically adds the store, adds the data, sets the store bit. It also searches all of the later, logically later locations, stages in this entry to see if anyone has the load bit set, or maybe even the store bit set. Right? If anyone has the load bit set, then that task got the wrong value, so it needs to be squashed. That's the idea. Basically, it's a store to load forwarding mechanism and also misspeculation checking mechanism. This is how you detect the misspeculation. And when a task commits, all of the task stores are committed into the data cache from the address resolution buffer. Right? So basically, this is very similar to the speculatively loaded and speculatively modified bits that we saw earlier with thread level speculation, right? Because it's essentially the same concept, except we're doing this not in the cache, not using the coherence protocol, but we're doing this with a separate data structure called the address resolution buffer. Okay, and if you'd like to learn more about the address resolution buffer, you can take a look at this paper. This is actually introduced a bank design for different processors, and you have 6 processors in this case that can be part of the design. But this is actually a centralized structure that is not that scalable. It may be easier to actually use the coherence protocol, some coherence mechanism to forward data values between different processors through memory, and also detect violations, memory dependence violations. Okay, so this was memory dependence violation detection, right? It's actually memory renaming, right? You have different versions of the same cache block with the same tag in different stages of this ARB entry, as we've seen, right? Basically, what ARB does is really memory renaming, right? The same location can have multiple different values, right? Except they have different versions depending on which task actually modified or executed them. But what it does not do is memory dependence prediction. Maybe you want to be more aggressive, because once you violate the dependence, you need to squash the task. It's already too late. You've already used the value. But can we predict that early on, right? You can actually reduce this intra-task flushes or squashes due to inter-task dependency violations by doing accurate memory dependence prediction. And we'll cover that next. The idea is predict, when you're doing a load instruction, a task, predict whether or not a load instruction will be dependent on a previous store, and predict which store it is, and delay the execution of the load if it's predicted to be dependent on a previous store. And if you can do this accurately, then you reduce the amount of squashing that happens between the tasks. And existing processors actually do this within the instruction window, because within the instruction window, the problem is similar, right? You may have a older store, that's writing to a location that a younger load is writing, but when the load executes, it doesn't know it. That store has not even executed yet. So that's the idea. And there are 2 seminal papers that I would recommend. One is Andreas Moshow's Dynamic Speculation and Synchronization of Data Dependencies that appeared in ISCA 1997. That's within the context of multiscalar processors. And the other is Christos Zemmer's Memory Dependence Prediction Using Store Sets that appeared in ISCA 1998. But let's briefly talk about handling of these store load dependencies, because this is actually important in an out-of-order execution processor too. Because in an out-of-order execution processor, you have the same problem. The problem is a load's dependence status is not known until all previous store addresses are available, right? And there are 2 key questions. One is, how does the processor detect dependence of a load instruction on a previous store? The second, how does the processor engine treat the scheduling of a load instruction with respect to previous stores? So that engine should not be here in the slides. How does the processor treat the scheduling of a load instruction with respect to previous stores? So let's take a look at the first question. How do you actually detect the dependence of a load instruction? Well, one option is to wait until all previous stores are committed, are done, computed their addresses, right? Then there's no need to check. This is the memory disambiguation problem. The second option is keep a list of pending stores in a store buffer and check whether a load address actually matches a previous store address. This is the load store queue that we've discussed earlier in the multi-core lecture. And if you actually take my class 447 in its out-of-order execution lecture discusses also the store queue, right? Basically, keep a list of pending stores. How do you actually treat the scheduling of a load instruction with respect to previous stores? Basically, when you get a load instruction, when do you schedule it? There are 3 options depending on different aggressiveness levels. The first is you can assume that the load is independent of all previous stores and schedule the load right away. This is what we were doing earlier, right, with a lot of the thread level speculation approaches that I've discussed. The second is you can assume load is dependent on previous stores. So the first one is the aggressive approach. The second one is the most conservative approach, which is you can assume load is dependent on all previous stores and wait until all previous stores and all tasks have completed. This is very bad, because this reduces your parallelism significantly, especially if you're designing a very large instruction window. The third option, which may be more intelligent, is to predict the dependence of a load on an outstanding store, right? Basically, this is the idea of the memory dependence prediction. So let's take a look at these 3 options. Assuming load is independent of all previous stores, the advantage is simple, and can be the common case, right? There may not be many stores that are producing values to nearby loads. So there is no delay for independent loads in this case, right? And previous research has shown that most loads are actually independent. The downside of this is it requires recovery and re-execution of load and depends on misprediction. And when the misprediction rate increases, the performance tanks in this case. The second option is to assume the load is dependent on all previous stores. There's no need for recovery in this case because you're really waiting conservatively until all previous stores have been resolved. And that's the downside. It delays independent loads unnecessarily. So this performs badly also. Third option is more intelligent perhaps. Predict the dependence of a load on an outstanding store. This is more accurate because it turns out load store dependencies persist over time across tasks also. So if you actually have a single instruction window divided into these tasks, let's say task 0 and task 4, it may be that this is doing a store and this doing a load, and this static store and this static load always are to the same address. Now if you can figure this out, this is a great prediction. If they're always to the same address, you know that when this task executes this load, if this store has not executed yet, you'd better wait for that store, right? And that's the idea that's proposed by these two papers, Moshowitz and Chrysos and Emmer. I'll refer you to those papers. I'm not going to talk about them in detail, but the mechanisms are basically built upon this idea. And why would this happen? Well, think about, for example, stack-based communication. It may be that you're storing a value onto the stack, and you're doing a function call, and you're doing a loads for that value from the stack, right? Because you don't have enough registers, for example, right? You're spilling the value into a memory from a register because you don't have enough registers, and this load is later loading or filling the value because you've spilled it earlier to memory. In this case, this is a very predictable dependence, right? So that whenever this load executes, you know that somebody else spilled it. Well, unless there are other writes to that location, but with spills and fills, there are usually no writes. So this is one of the reasons why memory dependencies persist between loads and stores. Okay, so the upside of this is it's more accurate, right? The downside is it still requires recovery and re-execution on misprediction, right? In fact, Alpha 21264, this is one of the readings that I recommended to you. Rick Kessler's the Alpha 21264 microprocessor paper that appeared in IEEE Micro in 1997. And if you have not read this, I would strongly recommend that you read it. The Alpha 21264 microprocessor that talks about a lot of the ideas that are introduced and implemented in the Alpha 21264, which was one of the fastest processors of its time. Basically, Alpha 21264, when it executed a load instruction, it first assumed that that load is independent of any store, so it went ahead and executed it. And later, of course, there's a mechanism to verify if that execution was correct, because it had load store buffers, as I discussed earlier, right? Whenever a store executed, it basically checked the load buffer and tried to find instructions that shouldn't have been executed. Tried to find instructions that are that have a larger sequence number than this than itself, and also that has an overlapping address. And the store detects that violation, and once there's a violation, the load shouldn't have been executed, and this loads that are found to be dependent are delayed. Basically, the load instruction is marked with a separate bit in the instruction cache saying that this load should wait for all of the previous stores to finish. So this was a hard measure, basically saying that you should wait for all of the previous stores in the machine to compute their addresses. It didn't associate the load with a particular store. It associated the load with all of the stores in the machine. But that's the Alpha 21264 did this memory dependence prediction, and that memory dependence prediction mechanism was actually quite effective in terms of reducing the, in terms of handling, basically quite effective compared to both option 1, which is aggressive, and option 2, which is conservative. And this is one example from Chrysos and Emmer paper. It shows basically the IPC on the y-axis and different benchmarks on the x-axis. It shows the conservative approach, which is no speculation. And if you see that the conservative approach is quite bad in most cases, the IPC is low. Actually, it's the lowest in most cases. It also shows the aggressive approach, which is the naive speculation. Basically, all load instructions are assumed to be independent of previous stores. And this is actually better in most cases compared to conservative approach, because you're actually, this points to the fact that many loads are actually independent of the store, so you'd better let them go. And this last one shows the potential of perfect prediction. You basically perfectly figure out if the load is actually dependent on a previous store with an oracle mechanism and simulate this, and wait only for that store to be executed to execute this load. And that actually provides the highest performance. So there's actually significant potential with perfect prediction compared to naive and both conservative and aggressive speculation mechanisms. Well, conservative handling and aggressive handling mechanisms. No speculation means basically the load waits until all of the previous store addresses are available. So this shows that predicting store load dependencies are important for performance. And actually simple predictors like what they propose in this paper or the alpha 21-264 predictor can achieve most of the potential performance. And I'll encourage you to read the paper as well as the alpha 21-264 paper to see the different predictors. And Christos and MM paper provides a good analysis of their predictors and other predictors. Okay, now we're done with multiscalar. I'd encourage you to do some comparisons of multiscalar. Basically, how does this compare to superscalar out-of-order processors? There's some comparison with a single instruction window that we've discussed, right? How does it compare to multi-core processors? This looks kind of like multi-core, right? Except we're speculatively parallelizing things. And except there's this weird thing going on with the register file, which is the round-robin communication, interconnection network that's tightly coupled to the register file. How does this compare to other chip multiprocessor and SMT, simultaneous multi-threading based thread-level speculation mechanism, like thread-level speculation that we've discussed earlier, right? The Stefan paper. So what is different in multiscalar hardware than in these approaches, and what is different in multiscalar software? I'm not going to go through this in detail, but one thing that I'll question is the scalability of fine-grained register communication. For example, the Colohan paper looks at does communication between different tasks through the coherence protocol that already exists. And there is no, the register-based communication is not there, right? Whereas with multiscalar, there is a register-based communication component. And this is very fine-grained, and this adds another point in the register file. This ring stop that goes into the register file adds another port into the register file, right? Now you need to synchronize accesses, arbitrate between accesses that's coming from the local processor as well as the ring that's going to the register file. So how does this scale to many processors? And this may be one of the Achilles heels of multiscalar implementation. This register file, very fine-grained register file communication may be difficult to implement in hardware because register file is a very important component that's on the critical path of the local processor. Now if you add one more port to it, maybe it becomes more difficult to design. And also you need to somehow do arbitration between requests coming from the local port as well as local ports as well as the side ports. The second issue of scalability is the scalability of memory renaming and dependence speculation. How can you scale this? And this is usually a big problem with thread-level speculation approaches. How can you actually make the memory dependence detection and violation detection mechanisms more scalable? With use of the coherence protocol, perhaps you can do that, but you can be as scalable as the coherence protocol, right? In multiscalar, the address resolution buffer is a centralized structure that's much less scalable than a directory-based coherence protocol, for example. So this is something to think about also. This is food for thought for you. Okay, let's move on to another speculative parallelization mechanism, which is helper threading for prefetching. And we've looked at this idea in 447 actually. But the basic idea is to pre-execute a piece of the program solely for prefetching data. Before, we were not solely for prefetching data. The multiscalar actually chops up the program and tries to merge the results in the end, right? Whereas here, we're going to use this additional context to purely prefetch data. And in this case, you only need to form a smaller version of the program that leads to cache misses to be able to capture the most of the benefit. Basically, speculative thread, this is the pre-executed program piece can be considered a thread, and it actually can be launched as a thread. And this can be executed on a separate processor or core, on a separate hardware thread context, or on the same hardware thread context in idle cycles during cache misses, right? This is, remember, run-ahead execution does this, right? When you get a cache miss, you keep executing the speculative thread to actually, you keep executing the program to actually generate prefetches in a speculative way. Okay, so this shows the generalized thread-based execution here, and these are some of the papers that I would strongly recommend for you to read. basically what we have, let's take a look at load in this case, but you can actually generalize this to any instruction that leads to some performance degradation. Let's say we have this load and this is our main program. The idea is while you're executing the main program, you also launch a thread, fork a thread, that executes a prune part of the program that is concerned with generating the address of this load, and that executes while the main thread executes, and that leads to a cache miss. And by the time this load actually executes in the main thread, a lot of the instructions are redundantly executed in the main thread, this load hits in the cache because this speculative thread already loaded the value into the cache. And as a result, you get some speed up, right? Now this load is not a miss anymore. That's the idea. And this idea is actually described in many different papers, and these papers are examples. Assisted execution is one example, for example. And you could do this for branch mispredictions also. Let's say you have a hard to predict branch. You can start a thread, you can speculatively launch a thread that executes the dependent instructions that lead to the outcome of the branch and produce a prediction. And once the branch is being fetched, you can read this prediction from a prediction buffer. And that's how you can predict the branch. And these papers concern themselves, Chappelle et al., simultaneous subordinate microthreading, Zilsensoi, execution-based prediction using speculative slices, that talk about some of these branch prediction issues also. So that's the generalized. With the generalized thread-based pre-execution, there are three key questions. Where do you execute this pre-computation thread? Basically, you can think of this thread that's generating results, prefetches and branch prediction outcomes as pre-computation thread, right? Where do you execute this? When do you spawn this pre-computation thread? When do you terminate the pre-computation thread? These are key issues. I'm not going to go into these in detail, but we'll talk about several options. You can execute the pre-computation thread on a separate core. This leads to the least contention with the main thread, right? Because the main thread is executing the main program, and pre-computation thread is executing the pruned version of the program that will hopefully generate cache misses, right? Or that will hopefully generate branch mispredictions. And basically, you have core 1, core 0, and core 1. You can execute the main thread here, and you can execute the speculative thread here. There's no contention between speculative and main thread in this case, which is good. But the downside is they're not communicating tightly together. They're communicating through the shared L2, for example. So communication may be hard to do this, and they are private L1s, right? You can do it on a separate thread context on the same core. You can have the main thread, you can have two thread contexts here, main thread and speculative thread executing here, right? In this case, there's more contention, so they can delay each other, these different threads, but the upside is they can more tightly communicate through the L1 cache, right? The prefetch is going to the L1 cache, right? You can also do it on the same core and the same context. Basically, I'm going to remove this, but you have the same core executing the main thread and also the speculative thread. And in this case, when the main thread is stalled, you can execute the speculative thread. So there is some contention in this case, but maybe okay if you're actually executing the speculative thread in the same when the main thread is stalled. The second issue is when do you spawn to pre-computation thread? Basically, you have a load instruction here, and where do you find the fork point? When do you spawn? If you spawn too late, maybe prefetch the thread that's executed reaches this load later than the main thread would reach, right? Or maybe it doesn't overlap the latency of the cache miss because main thread is going to reach that load anyway very soon. If you spawn too early, let's say you fork over here, and this thread, the speculative thread, reaches the load and gets a cache miss and handles the cache miss, but this main thread may never reach this load because you spawn too early. There's a bunch of branches over here, and this thread actually will never reach the same load because the branches are taken some other way, right? So too early is maybe bad also. And too early also can have other downsides. For example, this load may pollute the cache. This load may be kicked out before it's needed, or it may kick out some useful value that's needed over here, right? So it can cause cache pollution. Or you can spawn the pre-computation thread. Basically, there are trade-offs associated with them. These trade-offs are important to do, whether you're generating the threads in the compiler level, at the programmer level, or at the hardware level, right? Or you can do it when the main thread is stalled, right? You can spawn the pre-computation thread when the main thread is stalled, and people have looked at that also. One interesting paper about this is virtual multi-threading, and you can read that. I believe it's in ASPLOS 2004. this basically talks about the experiences of when a main thread is stalled, launching the prefetch thread on the same core in an Itanium processor. And of course, run-ahead execution, when the main thread is stalled, run-ahead execution kind of launches a speculative version of the same program, right? And then by checkpointing, you're actually generating a new thread, if you will, that is of the same program. The third question is, when do you terminate the pre-computation thread? Basically, you can do this with pre-inserted cancel instructions, or if the thread is not being effective anymore, you can terminate it, right? Maybe the main thread actually reached the point that the speculative thread is actually trying to prefetch for, right? It's too late at that point, so the main thread can say cancel. There can be a cancel instruction that actually cancels the speculative thread at that point. Or the runtime system can dynamically collect effectiveness and contention information about the threads, and based on that information, it can decide to kill the pre-computation thread. So there are a bunch of thread-based pre-execution issues that we're not going to be able to cover, but this is a fascinating topic also. And if you want to do a research in this area, this is I would strongly recommend this paper by C.K. Luke, who on tolerating memory latency through software-controlled pre-execution and simultaneous multi-threading processors. Basically, it discusses many issues in software-based pre-execution, and the goal of this paper is to actually generate prefetching threads for hard-to-predict data structures. For example, if you look at this here, the main execution can be going through a pointer chain, and pre-execution can be going through the other pointer chains. For example, if this is a hash table and you have many hash lookups, when the main processor, the main thread is doing a hash lookup on one key, the other processors can be pre-executing threads that are doing hash lookups on the future keys that may come up, right? And there are a bunch of other ones. Here, for example, multiple procedure calls. You can do function-based parallelization. When the main processor is executing one function, the pre-execution can be executing different functions. This way you can achieve function-level parallelization. And this paper talks about many issues, and I'm not going to go over this example, but this is basically an example that shows, this is actually from MCF. It's a memory-intensive workload from the Spec 2000 and 2006 workload suites. And this is an interesting workload. Basically, what's happening here is you have a while loop here that traverses. This is a vehicle scheduling program, by the way. You're basically trying to schedule vehicles to service customers. And what's happening is there's a linked list traversal over here, and for the different trips, you do many linked list traversals to find the right vehicle. And while you're doing this linked list traversal, the idea is to do pre-execution for the next linked list traversal, right? When you're doing the execution for this iteration, why don't you start the execution for the next iteration? So that's what this pre-execute start instruction does. It starts the pre-execution of this part as a next iteration. And the next iteration basically executes the next traversal for the next trip over here, right? And there's a pre-execute stop over here. And there's that basically ends the pre-execution for that next iteration. And there's, this pre-execute start actually starts. So this is the main thread. When you're executing the main thread, this is actually all of the threads. When the main thread is executing, when it gets to this point, there's a pre-execute start that starts from end 4, which starts from the next iteration, right? It sets up the next iteration and starts the next iteration in some other context. And the main thread keeps executing this iteration, and the pre-execution thread now keeps executing the next iteration, right? It also gets the pre-execute start. Now the question is, do you do nested pre-execute starts? In this paper, I believe they did not do it. But you could do nested pre-execute starts, right? The pre-execution thread can launch another thread. That's another pre-execution thread. Okay, so the pre-execution thread stops when it finishes the next iteration, right? And the pre-execution thread can also stop over here. If there is no next iteration left, there's another pre-execute stop over here. So this is how you can actually parallelize a program with pre-execution thread. And there needs to be some ISA extensions over here. For example, pre-execute start takes the start PC and some maximum number of instructions to execute potentially, and generates a thread ID. Pre-execute stop, the thread that's doing the pre-execution can be self-terminated, right? And pre-execute cancels mean the main thread, for example, when it does pre-execute start, it records the thread ID and can decide to cancel that thread later on. And there could be many reasons why to cancel this thread, and the paper talks about some of them. So this paper actually shows some promising results also. these are results from different applications with an SMT, a real SMT, simultaneous multi-threading processor at that time. And basically, if you look at this is the execution time normalized without pre-execution, and execution time normalized with pre-execution. So with pre-execution, you get significant performance benefits on some of these applications. So MCF gains 8%, for example, with 2 contexts. MST, the minimum spanning tree computation, gains about 36%. Ray tracing program gains 26%, 23%. Some programs actually lose performance because pre-execution consumes bandwidth and leads to contention, and there's a 5% degradation in compressed, for example. And the paper is a very interesting paper to read, so I would strongly recommend you to read it. There are a couple of other papers that actually discuss how to construct these backward slices, the threads, the pre-execution threads, and these Zillis and Soy papers are interesting reads over here. This is another example from one other Spec 2000 program, which is VPR, Virtual Praise and Route. The basic idea, this is one of the loops over here, and turns out this is a costly branch because it has lots of branch restrictions, and this is a costly cache miss. Let's take a look at how you actually construct. I'll just give you an example. I'll refer you to the papers for more details. But this paper talks about where you actually can insert the fork point to actually prefetch for this particular program, and you'd like to insert the fork point earlier, much earlier than this particular function before it's called in this case. And these are some of the instructions. Basically, the key question is when you actually try to generate a thread just to prefetch data or just to compute a branch outcome, do you need all of the instructions? If you needed all of the instructions between this point, this fork point, and the load, then having a pre-execution thread doesn't make sense, right? Because the main thread is going to execute all of those instructions anyway. Usually, actually, it may make sense if the speculative thread actually skips those instructions somehow, right? But in this case, we can actually reduce the program because not all instructions that happen between the fork point and the problem instruction actually lead to something useful to compute the address of the problem instruction or the outcome of the problem instruction, right? And this shows an example over here. There are many instructions between the fork point and the problem instructions, but you only need this many instructions, and you can count these 1, 2, 3, 4, 5, 6, 7 instructions, or maybe 8 instructions execute in the pre-execution thread to actually capture these, to actually compute what's needed to compute for these problem instructions. So you can prune the program significantly just to focus on these problem instructions. As a result, this pre-execution thread can be much leaner than the main thread, and it can execute quickly. Right. Now we will see that there could be other methods of constructing this pre-execution thread. Right. You could actually skip some instructions. You could actually value predict some instructions such that if you don't know the values, input values to the thread, you can predict the values coming into the thread. Because this is purely speculative, right? The goal of this thread is to improve the performance of the main thread. That's what you can achieve with purely speculative approaches. Run-ahead execution is an example of this approach also. Remember, this is a pre-execution method for prefetching purposes, and we've discussed this in an earlier lecture, and there's a Spring 2013 video that talks about run-ahead execution. This was my PhD thesis, and other people have worked on the problem. Dundas and Mudge looked at it in order processors in ICS 1997. But basically the key idea is when the oldest instruction is a long latency cache miss, the processor checkpoints the architectural state and enters a speculative processing mode. You could now consider this a speculative thread because its state is checkpointed. In run-ahead mode, instructions are speculatively pre-executed, and the purpose of pre-execution is just to generate prefetches, just like this helper thread. So run-ahead execution really generates a helper thread, uses the main thread as the helper thread. And the L2 misdependent instructions are marked invalid and dropped such that space can be made in the instruction window for other instructions that are independent. And the hope is that while this thread is executing, it executes some independent instructions, and it gets to some cache misses that wouldn't have otherwise been uncovered with the instruction window that you have. And these cache misses are prefetched, and run-ahead mode ends when the original miss returns. At that point, checkpoint is restored, and main thread starts re-execution from the beginning, from the point where the speculative thread actually continued execution to begin with. So normal execution resumes. Basically what happened was instead of stalling for this load, you switched in this run ahead thread, if you will, that executed quickly and got out of the and actually prefetched for the main thread. So let me give you this example, and I'll take a quick break right after that. Basically, with a small window, this is what happens. The processor computes and it gets a cache miss, and normally it stalls, right? And later it gets another cache miss and stalls again. With run ahead execution, the processor gets a cache miss and it enters this run ahead execution mode where it speculatively processes the instructions. You could consider this a speculative thread. And while the speculative thread is executing, it gets another load miss. And if this is independent, it can start servicing that load miss. And this miss starts being serviced in parallel with the original miss. Run ahead execution ends when this first miss comes back from memory. The processor's pipeline is flushed. And now the main thread, if you will, starts executing because the checkpoint is restored and the processor starts from the program counter of the load 1. Now load 1 hits because the miss is serviced, and the processor main thread continues execution. After that, at some point, the second miss gets complete, and when this load 2 actually executes, what happens is it hits in the cache, right? Because the speculative thread that got executed during the stall cycles actually prefetched data for the main thread that gets executed in the non-stall cycles, if you will. So as a result, you save significant amount of time with run ahead execution. So run ahead execution is another example of speculative parallelization of the program, just like a helper thread, except run ahead execution uses the main program. It doesn't really prune the program, it just uses the main program to actually generate cache misses. Now going forward, there are actually interesting research issues here, and I'd be happy to talk to you about it. How do you actually make this run ahead execution to be more effective? Can you actually prune this program dynamically in this run ahead mode to actually improve the performance and efficiency of run ahead execution? And that's a very interesting topic going forward. So I'll take a break here. We'll start with Slipstream processors at the beginning of the next video. Okay, we're back. We're talking about speculation and speculation to speed up a single program. And I'll cover two techniques that were proposed to do this. One is Slipstream processors. Slipstream processor is an interesting technique. Basically, the goal is similar to many thread-level speculation approaches, to use multiple hardware contexts to speed up single-thread execution. This is also called implicit parallelization, right? Implicitly parallelize a program. The idea in Slipstream is to divide the program execution into two threads, the advanced thread and the redundant thread. The advanced thread executes a reduced instruction stream speculatively. And the redundant thread uses results, prefetches, predictions generated by the advanced thread and speeds up using those results and ensures correctness. Redundant thread basically executes every single instruction, but it executes it faster because the reduced instruction stream provides some execution hints to the redundant thread. That's the idea. The benefit is by having these two threads, execution time of the overall program actually reduces. So the core idea is similar to many thread-level speculation approaches, except the key point here is to have a reduced instruction stream as the advanced thread. So with the speculative parallelization prefetching method that we've discussed earlier, pre-execution method, it's very similar to that method. There you can have a reduced instruction stream as well. This is also similar to Multiscalar, except Multiscalar doesn't reduce the instruction stream, if you remember. Thread-level speculation that we talked about earlier, from Stefan et al., they don't reduce the instruction stream. Here, instruction stream is reduced, and it's reduced dynamically. And we'll take a look at how it's done. And this paper talks about Slipstream processors improving both for performance and fault tolerance. It actually discusses how we can improve fault tolerance as well, right? Because if you redundantly execute instructions earlier in a reduced thread in some other processors, for example, you can try to when you redundantly execute the instruction, you can check whether the execution actually matches or doesn't match. And you can achieve some kind of fault coverage by this kind of redundant execution of instructions. Right. Okay, slipstreaming, the name comes from actually an interesting thing, one of those NASCAR or Formula One races, right? If you're a car racer, you would know this. Basically, this is from the paper. And this is a really nice analogy actually, because what you really have is one thread, one processor, one hardware context executing fast, and it's pulling this back slower hardware context such that it also executes fast at the same time. And this is the notion of slipstreaming Basically what happens is at speeds in excess of 190 miles per hour, there's high air pressure that forms in front of a race car and a partial vacuum that forms behind it. This creates drag and limits the car's top speed. A second car can position itself close behind the first one. This is called slipstreaming or drafting. Now this fills a vacuum behind the lead car, reducing its drag. Now the lead car can go faster as a result of this. And the trailing car now has less wind resistance in the front. And by some accounts, according to the paper, the vacuum behind the lead car actually helps pull the trailing car. Now the trailing car actually can move faster also. As a result, both cars can speed up by several miles per hour. The two combined go faster than either can alone. And that's the idea of slipstreaming, basically. This front processor, the advanced thread, can go fast and pull the slipstreaming, through slipstreaming, can pull the thread that's the redundant thread by generating results for it, prefetches, branch predictions, results, values. And as a result of these values, the back thread or the redundant thread can go fast. And once it goes fast, it figures out whether the advanced thread is doing something wrong or not, right? So it can figure out, it can synchronize with the redundant thread early on, advanced thread early on, such that advanced thread doesn't go into the weeds. Okay? So this is a nice analogy over here. Basically, slipstream processors detect and remove ineffectual instructions and run a shortened effectual version of the program or the advanced A stream in one thread context, and they ensure correctness by running a complete version of the program, redundant or R stream, in another thread context. Shortened A stream runs fast, R stream consumes near perfect control and data flow outcomes from A stream and finishes close behind. The two streams together lead to faster execution by helping each other than a single one alone. This is one possible hardware over here. I'm not going to go into this in a lot of detail, but this could be a multi-core engine. This is one core executing the A stream. This is another core executing the R stream. Basically, advanced stream what happens is there's a predictor, redundancy predictor and redundancy detector that figures out which instruction should actually be executed by the advanced stream. Advanced stream executes those instructions, puts them in a delay buffer, and redundant stream takes them out of this delay buffer and re-execute every single instruction, but it basically reuses the buffers, reuses the results coming from the delay buffer. And advanced stream fetches data into the L2 cache, and R stream can actually read data from that L2 cache. In this case, this is an old paper, but it talks about R stream state only, but it's actually, you can actually fetch data into the cache such that R stream's caches are warmed up by the time it gets to the instructions that's needed. So that's the basic idea. You could do it in a multi-threaded context. You could do it in a multi-core context like this. So the key question is, how do you remove instructions in slipstream processing? And this is actually a tough part of the slipstream processor. Basically, this IR detector detects ineffectual instructions and conveys them to the IR predictor. Ineffectual instructions are dynamic instructions that repeatedly and predictably have no observable effect. You would really like to remove that. For example, if a store is unreferenced after a point, you would like to remove it. And why could it be unreferenced? Because of compiler optimizations, right? So you can move the store somewhere before a branch, and you take the branch, and the store may not be needed here, right? It may really be needed on this path, right? But compiler optimization may move the store, hoist the store up there for some reason, right? Non-modifying writes, for example, if you have a silent store, if the store is writing the same value, that's an ineffectual instruction. You can remove its dependence chain also, backward dependence slice. Dynamic branches whose outcomes are consistently predicted correctly, these can actually be removed also, because you have the redundant stream to execute when you do the wrong thing, right? So a lot of loop branches and the instructions that are feeding those loop branches can be removed from this advanced stream, right? And the removal happens from the R stream instructions, right? IR predictor, basically this IR detector operates on the redundant stream, but IR predictor, when the A stream gets to a program counter, IR predictor says, oh, you should not execute it because these instructions are ineffectual, right? That basically removes the instruction from the advanced stream after repeated indications from the IR detector. There's some confidence mechanism. You can read the paper for more detail. But basically, A stream, advanced stream, skips these ineffectual instructions and executes everything else and inserts their results into the delay buffer. R stream executes all instructions but uses results from the delay buffer as predictions such that it can speed up. So what if A stream, one question with this kind of mechanism is, what if A stream deviates from correct execution? You can actually have a wrong prediction, right, in the advanced stream. Because A stream may incorrectly remove some instructions, or it can access some stale data in the L1 data cache that's not updated, right? How do you detect it? Basically, there can be a blanch or malview misprediction that happens in R stream, and this is also known as instruction removal misprediction. And once this misprediction is actually detected in the back processor, in the R stream, redundant stream, because redundant stream, remember, it's there for safety. It's really there for correctness, whereas A stream is really there for performance. Remember, we covered token coherence that decouples performance and correctness. We're really decoupling performance and correctness somehow here. The redundant stream is ensuring correctness. The advanced stream is ensuring high performance by prefetching results, by generating results for the R stream. How do we detect it? Well, basically, when on the R stream branch or value misprediction happens in R stream, at that point, A stream register state needs to be restored by copying values from R stream registers using the delay buffer or shared memory exception handler, and you can read the paper. And A stream memory state needs to be restored also, and the paper discusses one method of doing this, but there are other efficient methods. So you can imagine that the speculative written blocks by the A stream should not really get communicated to the R stream if they're really wrong, right? R stream basically needs to access memory to get the correct data. So basically, A stream memory state needs to be restored somehow. So there are several questions in Slipstream. How do you actually construct the advanced thread, and how do you speed up the redundant thread? The original proposal of Slipstream was limited in my opinion. Basically, it dynamically eliminates the redundant instructions, silent stores, and dynamically dead instructions, and dynamically eliminates easy to predict branches, which is good, but it leads to some complexity for this elimination. But there are other ways. You can dynamically ignore long latency stalls, just like granite execution does, right? When you get to a long latency cache miss, you ignore it and you keep going. This way you can create an advanced thread. And remember Sun-Rock processor that we discussed in the multi-core lecture? That's essentially what they did in a sense, right? You can think of that as an advanced thread and a redundant thread. And that's what they called it, right? You have an advanced thread that dynamically ignores long latency cache misses, in that case L1 cache misses, A thread. And you have an R thread that basically executes, and this A thread executes instructions that are independent of the cache miss, and the R thread's job is to execute instructions that are dependent on the cache miss. So this is another speculative parallelization approach, Sun's rock processor, right? We've already covered speculative parallelization with Sun's rock processor. Their goal was to tolerate memory latency better. And the way they did it was through the advanced thread and redundant thread. That's very similar to Slipstream, but advanced thread and redundant thread are constructed differently, and also they execute different instructions. So redundant thread is really not fully redundant in Sun's rock, because it executes only the deferred instructions. So you really partition the instruction stream into two in Sun rock. That's the main difference between Slipstream and Sun's rock processor. They call it the simultaneous speculative threading. Yeah. Simultaneous speculative threading. And I'd encourage you to read the Sun paper if you'd like to get more information. So you could do this that way. Or, let's go back to Slipstream. Other ways is you can statically construct an instruction stream that's based on profiling and that's based on some execution, right? That way you can reduce the size of the code that gets executed in the redundant stream. And there's a paper that I would recommend you to read from Rochester, a performance correctness explicitly decoupled architecture. If you're interested in doing research in this area, explicitly decoupled architecture. They use a compiler to construct the advanced stream, and that way they can actually make the advanced one of the processors simpler as well. And this was published in Micro 2008. I believe it's Alok Garg and Michael Huang, Garg and Huang. You can take a look at this paper. Okay. How do you speed up the redundant thread? That's another question, right? Original proposal actually reuses instruction results, control and data flow outcomes from the advanced stream. It turns out this is not that easy because you need to merge the results into the redundant stream, right? Somehow, and the redundant stream is executing out of order. How do you actually merge the results coming from the advanced stream into the redundant stream if you would like to do that? There are other ways. You can only use branch results, for example, to simplify things, or prefetch data as predictions. So original proposal actually didn't evaluate the impact of memory because memory latency was very short in the evaluated architecture over there. So if you'd like to actually look at there are a lot of issues in reusing some of these results, and I'd recommend one of the papers that we have written in IEEE Computer Architecture Letters about reusing the results of pre-executed instructions in a run-ahead execution processor. So this can tell you some of the issues in reusing the results of pre-execution with a specific case of run-ahead execution processor. And you know about run-ahead execution, and a lot of the concepts are similar, right? So run-ahead execution has a thread that's kind of looking forward, and that also can generate results, and that can actually, those results can be used by the main thread, right, instead of just the data values. Now it turns out it's difficult to do this, as explained in this paper, because you need to merge the results somehow. It's also not that effective because once you these results that are actually generated by the original thread or by the run-ahead thread, if you will, are actually for those instructions that are not necessarily on the critical path. The instructions that are on the critical path are actually dependent on the cache misses, right? Because cache miss takes much longer. So these instructions, reusing the results doesn't help that much in terms of performance, but it helps in terms of energy. Right? So it may be more interesting to actually design slipstream processors that actually where the advanced thread actually prefetches data for the redundant thread, and advanced thread also enables execution of mispredicted branches in the redundant thread in a more accurate way. So that brings us to something called dual core execution. Dual core execution is a similar approach to slipstreaming, except it designs the front processor and the back processor, or advanced thread and the redundant thread, in a different way. The idea is you have one thread context that speculatively runs ahead on load misses and prefetches data for another thread context. That's the front processor basically gets ahead of the back processor by not stalling on cache misses. That's the key idea. So if you look at this, you have two cores. In this case, it's like a chip multiprocessor. A superscale out of order core, superscale out of order core here. You have an in-order fetch. Basically, this front processor is like a normal processor. It doesn't skip instructions, but what it does is it does run-ahead execution on long latency cache misses, and all of its results are put into this result queue. If run-ahead execution is done, instructions that are dependent on L2 cache misses are not executed, and they're just placed into the result queue to be executed by this back processor. Back processor takes instructions in the order that comes from this result queue, basically in the dynamic execution order that has happened over here. It basically re-executes instructions, and it also executes instructions that were not executed because they were dependent on cache misses. It basically checks the result of every instruction correctly, one by one, and eventually retires the instructions over here. And if there's a mismatch between the execution that happens over here and the execution that happens over here, this back processor is the correct execution, and there's a flush that happens and instructions, the entire processor gets redirected. So the pipeline is a bit longer, if you will. This feels like a new pipeline stage in front of this back processor, because back processor now gets instructions from here. But now, if you have long latency cache misses, you can do run-ahead execution on them over here, and you can still keep executing independent instructions and keep feeding them into this result queue. And you can really have a very large instruction window, if you will, because this result queue is really a FIFO, right? It's a first in, first out queue. And you can scale its size to be much higher. Your processors don't need to be that large. In fact, they could potentially be in-order cores, right? They don't need to be superscalar cores. But basically, this result queue enables the look ahead of the window to be very large, because all of the instructions window in the window are all of those that are decoded by this core, until all of those and all of the instructions that are decoded by this core and they're executing in this cores are included in the window
these instructions that are sitting in the result queue are included in the window. And there are a bunch of instructions that are in the window of the back processor that are being executed. So they're also windows. So you can actually have a very large instruction window by decoupling these two processors that way. Okay, so let's take a look at this in a little bit more detail. Basically, the front processor, this is an instance of slipstreaming in my opinion, except it's a very different implementation. The front processor runs faster by invalidating long latency cache missing loads, just like in run-ahead execution. Load misses and their dependents are invalidated. Remember the invalid bits or bogus bits. Branch miss predictions that are dependent on cache misses cannot be resolved. Okay? So this leads to highly accurate execution as independent operations are not affected. Right? Independent operations can be executed in the front processor. They lead to accurate prefetches to warm up the caches, and they lead to correctly resolved miss-independent branch miss predictions. So if there's a branch miss prediction that's not independent of a long latency cache miss whose data is not available, then these mispredictions can be resolved and communicated to the back processor through the result queue. Misdependents, you don't want to stall on them. That's how the front processor gets ahead. Back processor, on the other hand, re-executes every single instruction that's coming from the front processor to ensure correctness and to provide precise program states. So it basically executes instructions that are dependent on misses, and it also resolves branch mispredictions that are dependent on long latency cache misses. And once that branch misprediction is resolved, the entire system, starting from the fetch unit of the front processor, is redirected such that you start from the right point. So the pipeline, the branch misprediction latency is actually longer than the pipelines of these two cores plus the result queue. So back processor makes faster progress with help from the front processor because it gets a highly accurate instruction stream. All of the branches that are independent of misses are resolved. And it gets warmed up data caches. Right? This is nice. Warmed up data caches are basically the benefit of run-ahead execution. Right?
Okay, we're going to wrap up speculation. We're going to talk about speculation to improve parallel programs. In the past few modules, we've actually talked about using speculation in parallel machines to improve the performance of sequential programs. And the idea was in general called thread level speculation, where you would take a single instruction stream and divide it speculatively into threads such that you can parallelize that instruction stream such that you can get higher performance out of it. Here, our focus will be on already existing parallel programs. How can we use speculation? The idea of doing something before you need it, or before you know you need it, to improve the performance of these parallelized multi-threaded applications. And here are a bunch of readings. We're going to cover some seminal readings, some interesting readings, and this is for your reference. This will be posted on the website, module website. And these readings start from Hurley and Moss's seminal paper on transactional memory and speculative lock elision and speculative synchronization papers, accelerating critical section execution with asymmetric multi-core architectures, which you've read. The original paper by Jensen et al. That introduced load linked store conditional operations, that was a precursor to transactional memory, and a bunch of papers. The last four papers are on recent implementations of transactional memory in existing processors by IBM, Sun, Intel, and AMD. We'll cover some of these readings as we go along. But what is the goal of speculation to improve parallel programs? Basic goal is to reduce the impact of serializing bottlenecks, in particular locks or critical sections. The goal is to improve performance and improve programming ease. And in this case, programming ease will be one of our utmost concerns. And that was a concern for sequential, using speculation to improve the performance of sequential execution as well, right? In that case, we didn't want the programmer to create the threads to begin with, but we wanted to use the underlying parallel hardware, multi-threaded or multi-core or multiprocessor, and have that hardware to automatically extract parallel threads out of a single thread of execution. Here, the goal was to improve performance as well as improve programming ease. The programmer didn't need to write parallel programs to exploit the underlying parallel hardware. Here our goal is very similar, except the parallel program is already written, but there are potentially some bottlenecks in it that can cause serialization. And it's difficult for the programmer to improve the performance of the parallel program to optimize these serializing bottlenecks, for example, locks, critical sections, barriers, bottleneck pipeline stages, which we had discussed in an earlier lecture on asymmetry. The key idea is, why don't we design hardware to do speculative execution to improve the performance of such bottlenecks, as well as improve programmer ease, because the programmer doesn't need to worry about these bottlenecks. One early example of this is transactional memory, which we will cover. In this case, basically the programmer specifies what should be executed atomically, and the runtime system and the hardware figures out how to do that. Basically, the programmer doesn't use locks, which are hard to program with, as we will discuss. The other example is speculative lock elision, which is basically transactional memory that is not exposed to the programmer, at least not exposed as much to the programmer. The programmer programs in locks, but the underlying system elides those locks when the locks are not really necessary. Basically executes critical sections in parallel if it's deemed that these critical sections actually do not conflict with each other. Martinez and Torellis' paper on speculative synchronization is very similar to speculative lock elision paper, except it is also applicable to barriers, and these two papers are worthwhile reading. And this is Rajwar and Goodman's final paper on transactional lock-free execution of lock-based programs. Again, the programmer programs using locks, and the underlying hardware ensures that those locks are executed concurrently. The critical sections that are protected by the same lock are executed concurrently, if they can be executed concurrently in a serializable, in a fashion without data conflicts. Right. So let's take a look at first speculative lock elision, and then we'll jump into transactional memory. These are the two approaches we will cover. And these approaches bear a lot of similarities with each other, and the key distinction is speculative lock elision is not exposed to the programmer, whereas transactional memory is exposed to the programmer, so it does change the programming model. And we will see, I will ask you to compare and contrast these on your own, and think about what are the advantages and what are the disadvantages of speculative lock elision versus transactional memory. So speculative lock elision, many programs use locks for synchronization. This is one of the synchronization constructs that we've covered earlier. Actually, there are other synchronization constructs like barriers and also pipeline parallel stages. And these synchronization constructs can also benefit from similar ideas, and I'll let you think about how to apply these similar ideas that I'll discuss to those synchronization constructs. And many locks, the observation is that many locks are actually not necessary. They're there for correctness, preserving correctness, but these locks are not necessary. Do not need to serialize execution. For example, there are two main reasons for this. One is you may need a critical section to protect some updates to shared data, but those updates may occur very infrequently. For example, you need a critical section to check, for example, let's say you insert an element into a list after checking some condition, and you need a critical section to protect that access, update of the shared data structure, but that update may not occur all the time because it's protected by a condition, and that condition may be infrequently true. For example, a store to a hash table may occur only infrequently during its execution, right? And it may only update the data in the hash table once in a blue moon, right? But you still need to protect that hash table because there may be a reader that reads at the same time that hash table is being updated, that store is happening, and every time you execute an access to the hash table, that reader needs to go through a lock and request exclusive access to the hash table, even though that store occurs only once in a blue moon. For correctness reasons, every critical section, every access to that hash table needs to be protected through that lock, even though most of the dynamic accesses are actually unnecessary. This is called dynamically unnecessary synchronization. Statically, the synchronization is necessary because at some point in time, there may be a case where a store, an update to a data structure can coincide with the reading of that data structure, but dynamically, many times over the execution of the data structure, you may not get any updates. Okay? That's one of the reasons why locks are unnecessary, because the store to the shared data structure doesn't occur frequently during execution, but reads may be much more common. And the second reason is programmers, actually the first reason occurs because programmers can be conservative also, right? They can actually protect the data structure overtly. The second reason, again, occurs because the programmers are conservative, because updates can occur to disjoint parts of the data structure. This is more about the programmer, actually. For example, think of a hash table and think of having multiple buckets in the hash table. Accesses to one bucket in the hash table can actually proceed in parallel with accesses, actually updates to another bucket, right? Because these two buckets in the hash table have nothing at all to do with each other. If I had to visualize what I have in mind, if you think of the hash table, basically hash table, you get an access, you get let's say an address, and you hash it in software and gets into a bucket. And let's say address 1 goes to this bucket, and let's say you're searching for address 1 in the linked lists that's associated with that bucket. This is one implementation of the hash table. This search of that address 1 in the hash table has nothing to do with, let's say, you're actually inserting address 2 into the hash table, but it happens to map to this bucket over here. And this insert operation into the hash table will update this linked list and not this linked list. So they have nothing to do with each other. But the programmer may protect the entire hash table with a single lock for programming ease, right? And that protection of the entire hash table serializes these otherwise potentially parallel requests, right, that go to different buckets, which means that you first need to use address 1 and search for it, and then only after that you can update address 2, which maps to a different bucket. So these have to be serialized because there's a single lock that protects the entire data structure. Now this happens because whereas because the programmer was actually conservative, right? The programmer can actually protect, have a lock for each bucket, right? Basically, the programmer can have lock 1 for bucket 1 and lock 2 for bucket 500, right? Or lock 500 for bucket 500, basically. The programmer can have as many locks as the number of buckets, or maybe some other granularity. And this way, now the programmer needs to manage all of these different locks in a fine grain, but now accesses to this bucket and to this bucket don't go through the same lock. As a result, you can eliminate this need for serialization because of mutual because you have the same lock, a single lock. Now you've eliminated that single lock. You've distributed the lock across the buckets. So this is actually easy to eliminate, but many programmers program conservatively. It's harder to program with finer grain locking, right? Finer grain locking is more difficult to implement because of the finer grain, exactly. You need to manage more locks. Whereas coarse grain locking is easier to implement for the programmer, but that leads to dynamically unnecessary synchronization. That leads to updates occurring to disjoint parts of the data structure, even though those updates having nothing to do with each other, and that leads to serialization. So these are the two reasons: stores occurring infrequently during execution and updates occurring to disjoint parts of the data structure are the two reasons why many locks are unnecessary. So the key idea, once you observe that many locks are actually unnecessary, speculative lock elision speculatively assumes that the lock is not necessary and executes the critical section without acquiring the lock. That's the key idea. And while during the execution of the critical section, the runtime system, or the hardware in this case, checks for conflicts within the critical section. If two instances of the critical section are executing concurrently, the speculative lock elision mechanism checks for conflicts, and if they do actually conflict with each other, rolls back the execution if the assumption was incorrect. The assumption is that the lock is not necessary, and those two executions of the same critical section can proceed in parallel because they're updating different parts of the data structure, or they're not conflicting with each other because there's no data conflict. And the system checks if that assumption is actually true, and if that assumption is not true, then the system rolls back execution and restarts. That's the idea. So these are actually from the paper, and the idea is described in the Rajwar and Goodman paper on speculative lock elision, enabling highly concurrent multi-thread execution. This is one of your required readings. And this shows dynamically unnecessary synchronization here, the two cases. Here, one example is you have lock and unlock, and the update is actually protected by an if
condition, and that if the condition is not usually satisfied, which that means that this critical section is usually not necessary. Right? Here is the example where I described on the board over here with the hash table. Basically, you have a single lock for the entire hash table, and you do lookups for x and y. If these x and y happen to map to different buckets, then there's no need for these two to be protected by the critical section when they're executing concurrently. Okay? So what are the issues? Basically, speculative lock elision, what it does is, the semantics of a critical section, speculative lock elision tries to elide the lock, right? It assumes that the critical section is not necessary. But the semantics of the critical section still need to be satisfied because it's there for correctness, right? And the semantics of a critical section is either the entire critical section is committed or none of it. So how does speculative lock elision actually provide that? Basically, there are many issues to solve in speculative lock elision, especially if you would like to do this transparently to the programmer. First, and the SLE paper talks about how to do this via hardware, purely in hardware. There are several issues. First, the hardware somehow needs to detect the lock, right? If there are lock instructions, this is relatively easy. But many ISAs actually lack the lock instructions. They have constructs that actually implement synchronization using different instructions, like compare and exchange, for example, in x86. And these instructions need to be detected to detect the lock, right? As well as detect the unlock, corresponding unlock. So you need to delineate the critical section boundaries. Remember in bottleneck identification and scheduling, we had the bottleneck call and bottleneck return. This was published in ASPOS 2012, and this was in our asymmetry video. Basically, those were there to delineate the critical sections or the bottlenecks. Here, if you're doing it purely in hardware, you need to somehow detect the lock. And the paper discusses that. I'd encourage you to look at that. The second issue is how to actually keep track of dependencies and conflicts in a critical section, right? Basically, how do you actually ensure that you know what the critical section read or wrote to? This is very similar to thread level speculation as we discussed earlier, right? How to actually parallelize single-threaded applications. Basically, you need to somehow keep track of what is read by a critical section and what is written by a critical section. And remember, in thread level speculation, what we did was we added extra bits to different memory locations, either the cache or address resolution buffer or a special store buffer like the address resolution buffer, saying this location was written or read by this critical section. Basically, each cache line had a read bit and a write bit added to the tag store, tag entry. We can do a similar thing, right? Basically, we can keep track of the read set and the write set of the two critical sections, right? And let's say you're executing lock A on this core, and there's unlock A, and another core actually starts executing lock A over here, and it needs to go to unlock A. If we're going to parallelize this, these parts will execute in parallel, and whatever is read here should not the read set, all the memory locations that are read over here should not overlap with the write set of this, and vice versa, right? The read set of this critical section should not overlap with the write set of this critical section, and also the write set of this should not overlap with the write set of this, right? Read sets can overlap with each other. The read set of this can overlap with the read set, but there should not be a conflicting write. There should not be a happen before relationship that is violated here, because the critical section semantics is either the entire thing is executed or none of it is executed. It cannot receive a value coming from this critical section over here. Okay? Basically, somehow you need to keep track of dependencies. And there are many ways of doing that. Actually, you could keep track of whether or not there's a conflict between these two critical sections by using the coherence protocol. Remember, thread level speculation used coherence protocol to detect the conflicts when some other thread actually requests this cache block as read exclusive. Then the cache block's read and write bits are set, and if any of them are set, This means that there's a data conflict and one of the threads is aborted, right? In this case, one of the threads will go back to the beginning of the critical section, right? Okay? How do you buffer the speculative state? This is very similar to what we've discussed, basically. If you're actually having writes over here, having stores over here, what do you do with those stores? You should really not expose them to any other part of the system, right? Because you do not know whether or not this critical section will execute or not. The execution should be atomic. You should only expose these stores at the very end of the critical section over here. And this requires buffering of the state, and we've discussed how to buffer the state, right? Address resolution buffer was one example. You could buffer in the cache. Of course, you need to change the coherence protocol such that this doesn't get exposed to other parts of the system. Okay? How do you check if atomicity is actually violated? How do you actually figure out the dependence violations, right? Using the coherence protocol was one example we've discussed earlier, what I discussed just now. Or there's an alternative strategy, right? Maybe you actually keep track of the addresses that you read and addresses that you've written to, and you accumulate that in some data structure until the end, until right before the unlock. And then at the very end, you compare those addresses to all of the other addresses that you've seen in the critical sections that are currently executing in the system. So this is a different approach. You don't detect the conflicts right away, but you actually detect them by comparing these sets, read sets and write sets. And you can actually implement these read sets and write sets using Bloom filters, right? You will be approximate, but approximate is okay over here, right? Why? Basically, whenever you can have a Bloom filter for the read set. Whenever you read an address, you set a bit corresponding to that address, and that bit vector can be small. Whenever you write to an address, you have another Bloom filter. This is the read Bloom filter, and this is the write Bloom filter. Whenever the critical section writes to an address, it writes, sets the bit corresponding to that address. And at the end of the critical section, these Bloom filters for this critical section are compared to the Bloom filters of all of the other critical sections that are currently executing in the system. And if these Bloom filters actually overlap somehow in a bad way, in a data conflicting way, which means read sets overlap with write sets and write sets overlap with write sets, potentially, then a conflict is detected and you know which transactions actually, or which critical sections conflict, and the system can abort one of them. So that's one other way of detecting conflicts. And people have proposed many different ways, and I would encourage you to think about different trade-offs associated with it. Later, how do you support commit and rollback? Basically, at the end, you need to somehow either commit or abort. Or do you abort early whenever you detect a conflict? If you detect the conflict eagerly. So there are many concepts over here. You can detect the conflict eagerly or lazily. And we will get back to this. Eager detection means whenever some other thread reads a cache block that is written or read, whenever some other thread basically requests this cache block in a read-exclusive manner, you know that there's a conflict, right? You can easily detect that conflict. That's the detection. Or you could detect the conflict at the very end, as I discussed to you. That's the lazy detection, right? This is the lazy detection approach. Detect the conflict at the very end of the transaction or the critical section. Eager approach, detect the conflict as it happens at that time. And then there is a question of when do you handle that? When do you handle the abort, for example? Whenever you detect it, or do you delay it at the very end? There's a trade-off here, right? If you abort a transaction, if you abort a critical section, right when you detect the conflict, that critical section may not finish, right? Because you may be using a policy that's not optimal. Because some other thread may always be conflicting with this critical section, right? You may run into starvation issues. So with eager handling of conflicts, you may run into starvation issues. But it's quick to react, right? When it figures out the conflict, there's no reason to continue this transaction or critical section, right? You can quickly react. And if the starvation is not an issue, this can be higher performance. Whereas lazy doesn't usually run into starvation issues because you can, at the end, handle in a calm head, right? See, oh, what have I done? Let me figure out which transaction or which critical section to abort, actually, so that I'm fair, right? So this is less starvation issues, but this could be could potentially be lower performance because the reaction time is slow, right? Basically, lazy conflict handling, lazy aborts can lead to slow reaction time. Right? But many of the issues over here can be classified as eager and lazy, and I'd encourage you to think about that also. Basically, how do you support commit and rollback? How do you actually, when do you actually abort, for example? How do you go back to the beginning of the transaction or beginning of the critical section? I keep using the words transaction and elided lock, speculative lock elision in a sense interchangeably because they're very similar concepts. But somehow you need to be able to support going back to the beginning. And usually that's supported via a checkpoint, register checkpoint. Because you don't update memory, you don't need a memory checkpoint. You buffer the speculative updates, right? You usually support that using a register checkpoint. And if there's a conflict, one of the transactions or one of the critical sections go back to the checkpoint. Right? So this is another important issue. Okay. So, okay. Basically, what we're really trying to do is to maintain atomicity. Right? If atomicity is really maintained, then all locks can be removed. So what are the conditions for atomicity? Data that's read is not modified by another thread until critical section is complete. Right? Or data that's written is not accessed, either read or written to by another thread until critical section is complete. So that's what conflict detection is all about. Basically, if we know the beginning and end of a critical section, we can monitor the memory addresses read or written to by the critical section and check for conflicts with other parts of the code. If there's a conflict, we can detect it using the underlying coherence mechanism, right? And that's what the SLE paper that I've assigned you actually talks about. How to use the underlying coherence mechanism to detect the conflict. This is very similar to what we've discussed with thread level speculation. It's a scalable approach to thread level speculation paper. So let's take a look at the implementation a little bit. I'm not going to go into a lot of detail on SLE implementation, but basically the processor checkpoints the register state before entering speculative lock elision mode and decides to enter speculative lock elision mode by detecting the lock. In speculative lock elision mode, if there's a store in the critical section, basically, the processor buffers the updates in the write buffer, in the store buffer, and doesn't make it visible to all other processors, but requests exclusive access for that particular cache block that it's trying to store to, right? That's the idea. So let me actually clean this up so that you can see a better picture of this. I'll get back to this eager versus lazy, so keep that in mind. A lot of the issues that we will discuss can be handled eagerly or lazily. Basically, the processor detects the lock, checkpoints the architectural state, and keeps executing, and there's a store, and this store goes into the write buffer, and also it sends a read exclusive requests in the coherence protocol, right? When there's a store or load that happens, this also sets the access bit. In this case, the paper talks about access bits. Basically, you have one bit called the access bit, not the read-write bits. You could have read-write bits, but this access bit is set whenever you do a store to a cache line or a load, right? And the system triggers misspeculation on some coherence actions. What are those actions? This is very similar to what we've discussed earlier. If there's an external invalidation to a block with access bit set, so if there's a coherence request that says invalidate this block, and the access bit is set, that means that there is misspeculation because somebody else is trying to access that block or actually write to that block or acquire that block that this particular processor executing this critical section actually has written to or read, right? Which means that there's a data conflict between two critical sections, or this critical section and other parts of the system, other parts of the code. Or if there's an exclusive access, not only invalidation, but also read exclusive. This is basically intention to actually write, to request a block with the access bit set, right? So that's the idea. And also, if there's not enough buffering space, this particular implementation triggers misspeculation. So what does that mean? Basically, you have lots of stores here, ... store, and eventually you run out of your write buffer entries, right? You cannot put this latest store into the write buffer entry because there are no write buffer entries left. Well, in this case, too bad, the system says. I'm going to trigger misspeculation, go back to the beginning of this particular critical section. Similarly, whenever misspeculation is triggered because of an invalidation or is exclusive return received to a cache block that has the access bit set, the processor goes back to the checkpoint it has taken at the beginning of the critical section, at the beginning of the SLE mode. Okay? And if end of the critical section is reached, which means that the processor detect unlock over here, if this end is reached, without misspeculation, all of the writes that are in the write buffer are committed. And this needs to happen instantaneously. Right? That's the idea. It needs to become visible to all processors as committed right away. All of their processors should be able to get those values without atomically. All of these stores need to happen atomically. Right? So that's the key idea. That's the implementation of speculative lock elision. It's very simple, conceptually easy, and let's actually compare and contrast this with accelerated critical sections. We've actually seen a different way of handling critical sections, which was accelerating them. Basically, whenever you get to a critical section, take the critical section and ship it to a large core such that you can get out of it fast. Right? SLE says, whenever you get to a critical section, basically elide the critical section. Keep executing and check for data conflicts. Right? There are advantages and disadvantages of both approaches conceptually as well as implementation-wise. In this slide, we talk about some conceptual differences. Accelerated critical sections has several advantages because it can speed up each individual critical section. Right? If you think about it, you actually speed it up by sending to a large core. At least that's the goal of accelerated critical sections. Whereas speculative lock elision is more for latency hiding. Basically, instead of serializing the critical sections, why don't we parallelize them such that we can hide the latency of these two critical sections? Right? That's the idea. So ACS is an advantage. And ACS works even in the presence of data conflicts. Right? If there are data conflicts, actually shipping them to a large core and serializing them there is a good idea, perhaps, because you don't compare it to SLE. Whereas SLE, speculative lock elision, if there are data conflicts between critical sections, it incurs re-execution overhead. One of the critical sections need to abort and re-execute. Right? So that's one advantage of ACS over SLE. It doesn't incur re-execution overhead since it doesn't speculatively execute critical sections in parallel. Right? And the third advantage is accelerated critical sections actually can keep shared data and locks in a single cache. It can improve shared data and lock locality. Whereas this doesn't exist in SLE because in accelerated critical sections, every critical section is executed in a single place, single core with hopefully a large cache. Whereas with speculative lock elision, every critical section is still executed in one, in a different core, right? Wherever it happens to be executed, basically. Okay, but accelerated critical sections also has disadvantages over speculative lock elision. One is whenever you ship the critical section to a large core or somewhere else, you need to transfer the private data and also the control to a large core. This reduces the private data locality, and which we've discussed when we talked about data marshalling in the asymmetry lecture. So I'll encourage you to go back and look at that, and this incurs overhead. This overhead is not present in SLE. Speculative lock elision, private data stays wherever the critical section is executed. Right. The other advantage of accelerated critical sections, it's whenever there's no conflict between the critical sections, speculative lock elision just makes sense, right? It basically keeps going, and it can parallelize these critical sections that would otherwise be executed serially. Accelerated critical sections doesn't do much about that. Even though there's no data conflict, the critical sections are serialized. And finally, accelerated critical sections use a mechanism that uses the large core and dedicates that large core for critical sections, and that large core can actually reduce parallel throughput. But we've discussed that if you actually add SMT, simultaneous multi-threading, to that core, you can reduce that effect of the loss in parallel throughput. So these are some conceptual advantages and disadvantages of accelerated critical sections. And these, some of the conceptual advantages and disadvantages are actually talked about over here. Basically, this is a section 8.2 from Suleiman et al.'s Accelerated Critical Section Execution with Asymmetric Multicore Architectures paper, which you read, and I'd encourage you to look at it again. Basically, it compares ACS to transactional memory, speculative lock elision, and transactional lock removal, and speculative synchronization. And these are actually approaches to parallelizing critical sections, synchronization constructs.
And the idea is, as long as the synchronization construct, the same instance of the synchronization construct, doesn't have a conflict with another instance, these can be executed in parallel. So these enable the hiding of the latency of the synchronization. Right? ACS actually is partly orthogonal to these approaches, this paper states, because when the critical sections have conflicts with each other, these approaches do not work because they need to roll back speculative execution to the beginning of the critical section, right? For all of the instances of the critical section except for one, right? Whereas ACS, regardless of however many data conflicts you have, it still obeys the locking semantics, right, in execution. As a result, it serialized the locks, serialized the instance of the same lock. Basically, the big difference is these are latency hiding mechanisms. Accelerated critical sections is hopefully a latency reducing mechanism for critical sections. And also the locality improvement that you get with ACS is not there with SLE or transactional memory as we see it, because accelerated critical section, these approaches do not execute synchronization constructs in a single place. So I'd encourage you to think about some of these advantages and disadvantages. And I'll not cover this, but this paper shows that accelerated critical sections for the critical section intensive workloads with not a lot of, with some data conflicts, actually accelerated critical sections performs better. But of course, there are advantages and disadvantages to these two different approaches, and potentially you can combine both, right? One accelerates the locks, and the other elides the locks, or synchronization constructs, let's say. The key question is, how do you actually combine the both? I'm not going to give you the answers, but I'll pose the questions because these could be actually very good projects if you're interested in that as well. Can you do better than both? How do you actually decide whether to accelerate a lock or elide a lock? For example, I'll give you a hint. If you can actually predict when you get to lock whether you will have a data conflict, and if the outcome of that prediction is yes, it's likely that if I execute this critical section, if I elide this critical section, I'll have a data conflict. And if it's on the critical path, then you ship it to the large core, right? Because it's important. If it's a critical section, it's a bottleneck critical section. Whereas when you get to the critical section, the prediction is that, oh, I haven't seen a lot of data conflicts for this critical section. Let me keep executing. Let me elide this. Then you pick speculative lock elision. So perhaps you can do better than both by combining both ideas. And sometimes you may want to elide the lock. Sometimes you may want to accelerate the lock. And sometimes you may want to do nothing about it, right? Because shipping it to a large core may incur more overhead than the benefit you get from the large core. Okay, so I've covered speculative lock elision, which is a very promising way of actually improving the performance of parallel programs by hiding the latency of critical sections. And we have already looked at accelerated critical sections, which was actually not a speculative mechanism. So the difference between speculative lock elision and another difference, more implementation difference, is speculative lock elision is speculative, whereas accelerated critical sections is really not speculative because it really obeys the locking semantics. It doesn't really try to parallelize the locks, whereas speculative lock elision tries to parallelize the same lock. So let's go back to some of the four issues that we've seen in speculative parallelization before. Remember, there were four issues in speculative parallelization, and these are actually applicable to speculative lock elision as well. These were applicable to speculatively parallelizing a single-threaded program as well. So first issue, how to deal with unavailable values. Do you predict them or do you wait for them? Well, actually in speculative lock elision this doesn't happen because the program is already parallelized, and because you're not cutting the program already, the values are available. You're not really making things, you're not really trying to partition the program at a point where some value is not available. The value is already available, you're trying to elide the lock. Right? So that's the idea. So this issue doesn't exist as much in speculative lock elision. Although you could view the potentially dynamic data conflicts between two critical sections as an unavailable value for another instance of that critical section. But we're not going to view it that way. We're going to view that as a conflict. The second issue is how to deal with speculative updates. Are you actually eager when you do speculative updates, or are you actually lazy? Eager means basically you update the original location and you log the old value. And then when you abort, then you need to undo from the log. That's a very aggressive way, right? Eager's advantage in this case is you update the original memory location such that that update becomes visible. You don't need to deal with re-updating the location at the very end. Now, lazy means you buffer your updates somewhere and do not expose them yet to the original location. Now you have multiple copies, right? If you do buffering, you have multiple copies. If you do logging, then you have the original copy is always at the same place, but you have a backup copy that you need to go back to in case there's a data conflict. With buffering, you're lazy. You basically postpone the updates until the end of the critical section, postpone the stores until the end of the critical section. The advantage is you don't expose them quickly. The disadvantage is now you need to ensure that at the end they're all exposed at the same time. Right? That's the idea. So eager versus lazy applies over here too. And in the approach that we've discussed, speculative lock elision does it lazily. Right? How to detect conflicts? Again, we've discussed that. Do you detect them eagerly or lazily? Right? Do you detect them right away, or do you actually lazily keep track of reads and write sets, and at the end of the critical section, you compare the reads and write sets and to figure out whether or not there are conflicts. And finally, how and when to abort or roll back or commit. When do you decide that? How to abort? Do you abort eagerly or do you abort lazily? Eager abort means you abort right when you detect the conflict between the transactions or between the critical sections. Lazy abort means you wait until the end of the transaction. At the end, you figure out which transaction to abort. Right? Here, because you can always abort one or the other. Right? It's not clear which one to abort. And sometimes it may not be, it may be very unclear when you have many different transactions running at the same time, many different critical sections instances running at the same time. How to commit is easier actually because you need to commit at the very end, right? And that's important. There's one other issue, basically whom to abort actually is important because and when to restart is also important because you want to ensure starvation freedom and you want to ensure fair progress for different threads for different transactions. You don't want to abort all the time the same poor transaction, right? If that's the case, you'll run into starvation issues. So doing this conflict handling in a way that's fair as well as high performance becomes an interesting research area in speculative lock elision as well as transactional memory approaches that we will talk about later. Basically, the takeaway is eager versus lazy approaches are possible for each of these issues, and I encourage you to think about different approaches and their trade-offs. And there has been a lot of literature in this field, at least in transactional memory, maybe less so in speculative lock elision, but in transactional memory that deals with these 4 different questions in speculative parallelization. So let's take a quick break, and then finally we will cover transactional memory, and after that we're going to finish our module on speculation in parallel machines. Okay, now that I've covered speculative lock elision, I'll briefly cover transactional memory, but transactional memory is actually speculative lock elision exposed to the programmer, and that's actually a good way of thinking about it. It does change the programming model significantly because it doesn't keep the lock-based programming model, but a lot of the ideas of transactional memory are actually very similar to speculative lock elision that we've discussed earlier. So I'm going to go through this relatively quickly and defer you to the papers that I'll discuss, as well as some of the other literature that we will put up online. But I'd be happy to take any questions related to this and give you potential pointers in terms of potential research topics. But the basic idea is, remember, we want to keep atomic execution of critical sections. And the basic idea here is programmer specifies what code should be executed atomically as transactions. And hardware and software guarantees atomicity for these transactions. Which means that the programmer doesn't need to deal with locks anymore, right? The programmer, all they need to do is delineate the transactions or what code needs to be executed atomically. That's it. There's no need for the programmer to lock individual buckets of a hash table. Remember that hash table example that I gave you earlier? there's no need for the programmer to do fine-grained synchronization, fine-grained locking. The programmer can say atomic hash table update, right? Atomic hash table read. I guess so there's a bunch of code that does hash table reading somehow, and a bunch of code that does hash table updating over here. And this doesn't need to be atomic. Another way of thinking about it is begin transaction and end transaction at the very end. Right? You could use begin transaction and end transaction. Right? And somehow the hardware and software guarantees that this entire piece of code is executed all or none. And how does it do that? Well, similarly to what we've discussed earlier. This is motivated by the difficulty of lock-based programming. Lock-based programming is not easy, as we will discuss in the next slide. Programmers make mistakes because they need to protect everything with locks. And if they want to get high performance, and locks cause serialization, right? That is a form of blocking synchronization. When a thread acquires the lock, all of the threads that need to acquire that lock need to block. Basically, locks lead to blocking synchronization. Threads block, waiting for the lock. And because of this, you want blocks to be small as possible, the critical sections. But if you want to make the critical sections as small as possible, it becomes harder. Now you get into buggy programs. This is the fundamental trade-offs that we've discussed earlier. Much of parallel computer architecture is about enabling the programmer's job to be easier when writing high-performance parallel programs. So that high performance comes from reducing the size of the locks, and it's difficult to reduce the size of the locks because now you get into bugs. What if you incorrectly exclude something out of the critical section, whereas that is important for correctness to be inside the critical section? Whereas, one way of getting rid of that problem is having a single lock for the entire program, right? For main, beginning of main, you say lock. At the end of main, you say unlock. And all the threads do that. Now this is terrible for performance, right? Because every thread is serialized with every other thread. You don't want that. That's really bad. Transactional memory kind of gives that illusion in terms of programming. But it's really easy to program, the first one. You don't need to reason about any conflicts, any potential shared data updates at all. Transactional memory kind of gives that illusion to the programmer, right? Basically, you can have a large atomic block, and the underlying hardware or the software determines which atomic blocks can be executed concurrently without violating atomicity. That's the idea. Transactional memory is also motivated by the lack of concurrency in blocking synchronization. I mean, we've kind of talked about this, right? Blocking synchronization leads to lack of concurrency because you need to have serialization. But there are many cases where serialization is dynamically unnecessary. If you had atomic constructs like this, begin transaction and end transaction, then the runtime system can decide which transactions can be executed in parallel in an underlying manner. There's no reason for the programmer to synchronize, serialize these different accesses that are that do not require necessary synchronization dynamically. So another form of term, basically, this blocking synchronization is locks, whereas non-blocking synchronization is transactional memory, or because when you get to a critical section, atomic block, you don't block, right? You don't actually wait for someone else to release the lock because there is no lock, okay? Also, transactional memory is called optimistic concurrency, whereas locks are called pessimistic concurrency. Why? Because locks are really serializing every access to that shared data structure they protect, right? This is kind of pessimistic, right? What if those accesses do not conflict with each other, right? As we've seen earlier. Whereas transactional memory is optimistic because there's no need to really serialize the atomic blocks. Execute the blocks, and if there's a data conflict, you detect that conflict. It's kind of optimistic in the sense that it works best if there are no data conflicts, and that's kind of the assumption, right? The data conflicts is rare, so we're going to elide the locks. We're going to execute these transactions in parallel. And only if they conflict with each other, we're going to detect that conflict and roll back one of them. Okay? So let's take a look at these locking issues in a little bit more detail. Locks are not great programming constructs, even though they work well. They have some issues, they have some problems that make it difficult or low performance to program with them. Basically, what's a lock? Lock is an object only one thread can hold at a time to enable synchronization. For example, you can have a lock for each shared data structure, or you can have a lock for a portion of a data structure, maybe individual nodes in a linked list. That'll be hard to program, right? Maybe individual buckets in a hash table. That'll be hard to manage. The usage is a thread waits for acquiring the lock, which means that it can block for a while, waiting for the lock, and then it acquires the lock. It basically writes to a memory location, for example, or it can be a counter-based lock. You can increment a counter. It accesses the critical section after that, and once the critical section code is done, it releases the lock. That's the model. This leads to several issues. One is correctness issues, and the other is performance issues. And we'll take a look at both. Correctness issues, if you want high performance, well, you may sometimes need to forget a lock, right? This leads to underlocking, right? Basically, this leads to data races, and sometimes you get incorrect behavior because you may have forgotten a lock. Why? Why do you usually forget a lock? Well, you may be careless, yes, but sometimes you actually forget to protect some part of the code that needs to be protected because you're really trying to optimize performance in this code. And to optimize the performance in this code, you want to minimize the serializing constructs, which means that you want to get rid of those critical sections that are large. That leads to underlocking, that leads to data races, and that leads to bugs that are necessarily, that may actually lead to incorrect execution. Right? So data race means basically you have accesses to shared data that is done concurrently by different threads. This is not necessarily a bad thing, right? This may not be a bad thing. For example, accesses to locks are actually data races, right? When somebody is writing, some other thread may be reading from it, and that data race is necessary for synchronization. But for regular shared data, it may not be a good thing because when one thread is updating that shared data, you may not want another thread actually reading that shared data. That's the whole purpose of synchronization. For example, when one thread is inserting to a linked list, you may not want that other thread to read from that linked list, especially if that read and insert will not be consistent. Right? Will not achieve the semantics you would like to achieve with that read and write. The second correctness issue is acquires in different orders. I'm not going to go into this in detail, but if you're actually protecting multiple different structures, you may get into a situation you have different orders of acquires. One thread may acquire lock A and wait for lock B in that order, because the control flow happens to take that thread that way. So it's going to acquire lock A, acquire it, and then can wait for lock B. Another thread can acquire lock B, and it gets to wait for lock A, but this thread is holding lock A, and this thread, so it cannot make progress. Whereas this thread is waiting for lock B, and this thread has already acquired lock B, so this cannot make progress. Too bad. Now we have a deadlock, right? No thread is making progress. This happens because you have different locks for different structures, and if you had a single lock, it could reduce your concurrency, right? That's the problem. You may actually want to protect only this data structure sometimes, only this data structure sometimes, and then you want both of the locks to be acquired when you want to protect both of the data structures when you're doing something with both of them. So this leads to deadlock. Whereas if you have a transaction begin and transaction end, this doesn't happen because there is no acquire and release. There are no different locks. Basically, somebody guarantees that atomic execution is satisfied. Let's take a look at the performance issues. Well, as I told you, locks lead to conservative serialization. There is also overhead of acquiring the locks, right? If some other thread is actually holding the lock, that lock needs to be brought to the cache of this other thread that's executing in this other core. So it takes time to acquire the lock. So there's ping-ponging that happens because of the locks. It's difficult to find the right granularity of locking exactly because of what I discussed, right? If you actually make the locks coarse grain, it's easier to program, but lower performance because of the overheads. Whereas if you make the locks fine grain, it's harder to program, and the performance is higher potentially, but there may be correctness issues. And blocking synchronization is the cause of a lot of these issues. So let's compare and contrast locks and transactions. Remember, in locks, we had underlocking issues because the programmer needs to minimize the locks because they cause serialization. Transaction can help this because the interface is simpler, right? The programmer doesn't need to reason that much about what is really shared data and what's not shared data. They do need to reason about what needs to be executed atomically, but they can be a little bit relaxed about it because atomic means all or none. And if the programmer wants, the atomic can be a larger code section. Whereas with locks, you have blocking synchronization, so the programmer, it's difficult for the programmer to reason about that interface, right? And reason about what will happen when they reduce the size of the critical section, right? Locks have deadlock due to lock ordering, whereas transactions have no ordering of locks because there are no locks to begin with, right? As we discussed. There can be no deadlocks in transactions unless the transactional memory manager somehow does a wrong thing. But that's not the responsibility of the programmer. Right? Locks lead to blocking synchronization, whereas transactions are non-blocking, as we discussed earlier. Right? Basically, whenever there's a conflict, one of the transactions actually abort, and the transactions go into the transaction is executed optimistically, as we've discussed. And finally, locks have conservative serialization. They have forced serialization all the time, whereas basically for different instances of the same critical section, they're conservatively serialized even though serialization may not be necessary dynamically. Whereas transactions serialize only on conflicts. Right? The conflict is detected dynamically and serialization is then forced if there is a conflict. Whereas if there is no conflict, two transactions can execute concurrently. And that's the idea of optimistic concurrency versus pessimistic concurrency that we've discussed. So transactional memory, if you think about it, it allows arbitrary multiple memory locations to be updated atomically in an all or none fashion. And there are several basic mechanisms which we've already covered actually, so I'm going to briefly go through these. One is you need to provide isolation and conflict management. You need to isolate these two transactions from each other. Whenever this transaction is executing over here, this transaction should not see its state because this is not updating that state. And the other parts of the system should not see the updates, which means that you need to do buffering. Right? You need to track reads and writes per transaction. And you also need to detect conflicts between transactions. And we've discussed this earlier. Version management, you need to record new and old values because you don't want them to be exposed, new values to be exposed to the other parts of the system. And we've talked about this in detail when we talked about SLE, speculative lock elision, earlier. And there are eager versus lazy ways of doing that, right? You could record the new values in a log or in a buffer, right? Okay, and atomicity is another mechanism that needs to be provided. Basically, the transactional memory provides a mechanism for committing new values or aborting back to old values. You have all or none semantics in a transaction. And that's what's really important, just like speculative lock elision as we discussed earlier. So issues are actually the same as other speculative parallelization schemes. Remember the four fundamental things? Actually, I have three over here because one of them doesn't exist. And you can think about what that is while you're listening to this video. Logging and buffering, conflict detection, abort, rollback, or commit. And remember, these were the four things. How to deal with unavailable values. Do you predict them or do you weight them? This doesn't exist over here, really, because the values hopefully are available. But how to deal with speculative updates? Do you do logging or buffering? How do you detect conflicts? Do you do it lazily or eagerly? Do you use the coherence protocol? Or do you actually keep track of read sets and write sets and potentially Bloom filters? How do you, and when do you do the abort and rollback and commit? And also, who do you abort? On a conflict is important. Do you do it eagerly and lazily? Do you have a manager that actually manages which transactions, which threads should commit its transactions? What kind of quality of service and what kind of fairness guarantees do you give to the transaction manager? Basically, these are all can be considered transaction scheduling, if you will. Which transaction do you actually abort? Which transaction do you commit? Which transaction do you restart? And again, we've covered this a lot in the speculative lock elision lecture. You can go back to it, and a lot of the issues are similar with transactional memory and speculative lock elision. But there's an abundant set of papers that look at conflict management and transaction scheduling in transactional memory, and I'd encourage you to look at those if you're interested in this. There are many variations of transactional memory as well. This can be implemented purely in software, which means that the runtime system somehow ensures that you actually satisfy these atomicity semantics in the transaction, right? So the upside of this is there are no virtualization issues, right? All of the addresses are virtual. If you actually interrupt the process, well, you can actually keep track of everything in software, right? Basically, what are the issues with actually virtualization? Let's say you get an interrupt in the beginning, in the middle of an atomic code block. It's okay if you have everything handled in software, right? Because software actually, the state of this program is saved somewhere. So all of the information that you keep track of about the read set and the write set are saved in software. So for example, when you do read, write, if you have software transactional memory, these need to be kept track of in some data structures that keep the read set and the write set, right? And these data structures are part of the program, and when the program is interrupted, those get saved somewhere. So automatically virtualization is handled. The downside of software transactional memory is its high performance overhead. All of these operations that we've discussed earlier need to be done in software. Conflict management, read-write set tracking, abort management, all of them is purely software. And that adds a lot of overhead into the system. On the other hand, hardware, the upside is low performance overhead. Everything is done in hardware. Coherence protocol specifies, for example, is modified such that you abort transactions easily. The downside is now you need support for virtualization in hardware. Right? For example, what if your buffering for writes are not enough in hardware? What do? You don't have enough buffers for writes? Well, you may need to virtualize. If you want to support a large transaction that writes 1 million memory locations, where do you write those? Well, maybe you virtualize those buffers, right? Now this becomes more complex. Virtualization is also needed when you get a context switch in the middle of a transaction. What if you have a long-running transaction, right? And you want to take the context switch, and the transaction is running in hardware. Now you have these hardware structures that are buffering the data. For example, the read-write bits in the cache. What do you do with them? Too bad, you cannot blow them away because they belong to this transaction and they affect correctness, right? So when you get to a context switch, do you actually abort the transaction then? Well, that may not be a good idea because the transaction may be actually a long transaction. So what if you will eventually need to complete it, but what if it gets a context switch again? So you run into these issues of virtualization when you have pure hardware transactional memory. And this actually should be HTM over here. So I'm going to modify the slide right here, if you will, and actually even save it. Okay. So, and what happens when you do I/O within transactions, right? When you do I/O, you usually context switch. How do you handle that? How do you serialize these transactions when they're hardware, when the transactional memory is purely in hardware? So because of these issues, again, you have upsides and downsides as you see between software and hardware. People have looked at hybrid hardware-software mechanisms, and as you can imagine, it's a heterogeneous approach. Basically, the basic idea is when buffering is enough and there's no I/O or context switch, use hardware transactional memory such that you get low performance overhead in executing transactions, and switch to software transactional memory to handle long transactions and buffer overflows and I/O and context switches, basically. That's the idea. And I'd encourage you to read papers related to it. There's been significant literature on this. Let's go back to the beginnings a little bit and talk about some of the initial TM ideas and current implementations very briefly, and then we'll conclude transactional memory in particular and speculation in parallel machines in general. Transactional memory is actually inspired by load-linked store conditional operations. And Jensen paper from Lawrence Livermore National Lab Technical Report in 1987 is the first one that introduced this. But the basic idea is to have an instruction that does an atomic update of a single cache line without any lock. We don't want any locks. We want to update the single cache line. How do we do it with some new instructions? And that's the idea of load-linked and store conditional operations. This is used to implement non-blocking synchronization in existing ISAs. Alpha and MIPS are some of the first ones to implement it, but ARM and PowerPC have this. x86 has a form of it. The basic idea is you have two instructions, load-linked. Load-linked instruction, LL, returns the current value of a location. Let's say load-linked memory location A into R1. Okay? And then a subsequent store conditional to the same memory location will store a new value only if no updates have occurred to the location. Okay? And then you do store conditionals, new value, right? And then you give it R1 and then memory location A, right? Okay? And this basically ensures that if someone has updated the memory location A between this load and store, you figure that out, right? Because this store doesn't succeed if someone has updated. Now you can check whether the store succeeds. I've butchered the semantics over here, but you can check if the store succeeds, and if the store doesn't succeed, you can keep doing this. If no success, which means that somebody has perturbed with the memory location, there was an update to the memory location and the value of the memory location changed, which means that somebody else must have changed it, then you keep going back, and this is the programmer needs to do this, of course, loop, and keep loading. Right? Whereas store conditional, if it succeeds, then you can keep going, keep executing. That's the basic idea. You enable the lock-free atomic update of a single cache line using these two instructions. And these instructions are supported. Then the key question is, how do you actually do lock-free atomic updates of multiple cache lines? And that's where transactional memory comes in. Hurley and Moss were in their seminal ISCA paper, which is assigned to you as required reading, introduced this idea of transactional memory. And you can view transactional memory is a way of providing atomic updates for multiple cache blocks or multiple words at the same time. In their implementation, originally, instructions explicitly identified transactional loads and stores, and there was a dedicated transaction cache for buffering. Basically, buffering was not done in the cache, but there was a dedicated transactional cache. And unfortunately, size of the transactions were limited to this transaction cache. So if you had too many stores within a transaction that overflew this cache, too bad. You would abort that transaction and execute it in a non-transactional way. Or execute in a more protected way, right, in a lock way. Okay? So this is an example from the Hurley and Moss paper. I'm not going to go into this in detail, but basically what they say is our transactions are intended to replace short critical sections. For example, a lock-free data structure would typically be implemented in the following stylized way. Instead of acquiring the lock, executing the critical section, and releasing the lock, a process would use LT or load transactional to read from a set of locations, use validate to check that the values read are consistent. So there's no lock. You see, you start doing load transactional. And then you do validate to check that the values read are consistent. Validate means if no one has updated them, that's okay. They're consistent because they check the transaction cache. Use store to modify a set of locations, and use commit to make the changes permanent. If either the validate or the commit fails, the process returns to step 1. There you go. That's the atomic part of it. Okay? So you can read the paper in more detail. This is the beginning of transactional memory. Currently, there are many implementations of transactional memory. Some of them are in machines that have never seen the day of light. Some of them are in machines that you can actually buy and use today. Sun Rock was one of the earliest implementers of transactional memory. Remember, this was a machine that implemented run-rate execution as well. And actually, the speculative lock elision and run-rate execution had similarities that bear with each other. That's one of the reasons why Sun Rock amortized the cost of either one of them by implementing them together. They implemented run-rate execution and speculative lock elision, or transactional memory. Why? Because transactional memory checkpoints the architectural states and keeps running ahead speculatively as well. Whereas run-rate execution has a very similar approach. It basically checkpoints the architectural state and keeps running speculatively the program, right? So I recommend this paper that talks about early experience with a commercial hardware transactional memory implementation, which is Sun Rock's implementation. IBM Blue Gene, which is a supercomputer, also implements transactional memory, and this is a recent packed parallel architectures and compilation techniques paper that talks about its evaluation of hardware support for transactional memory in IBM Blue Gene. IBM System Z, another processor that's used in mainframes of IBM, implements transactional memory to ease programmers' job. And these are actually very parallel machines. That's one of the reasons they implement transactional memory. The idea is to ease programmers' job and also improve programmer productivity in programming these machines. So they have two types of transactions: best effort transactions. In this case, the programmer is responsible for the aborts, and guaranteed transactions that are guaranteed to execute. So guaranteed transactions are guaranteed to execute. They're subject to many limitations. For example, this transaction site length should not be more than this. Now, why are there these requirements? There are these requirements because the hardware structures, this implements hardware transactional memory. The hardware structures that are there to support transactions are of limited size. And if the transaction, for example, has a write set that's greater than the buffering that's implemented in this processor, too bad. The transaction will execute incorrectly, right? The programmer needs to guarantee that the transaction satisfies some of these requirements. And if that's the case, the hardware guarantees that the transaction will always execute correctly and atomically. On the other hand, if the programmer cannot guarantee that, they should use best effort transactions. The programmer is actually responsible for aborting transactions and doing their own conflict management. Now, as you see, this makes it a little bit harder to program with transactions. It's not that easy anymore, right? It was the easy abstraction, atomic, and executes beautifully atomically. Now, if you tell the programmer, you need to actually figure out how many cache blocks you're touching in your critical section. And based on that, I will guarantee you correct execution or not. Well, that makes it a little bit harder to program still. It's a different kind of reasoning that's required from the programmer at this point. Now, this may still be useful for many programmers that try to optimize their code because it can ease their job in doing performance optimization. But for the average programmer who has no idea potentially about how many cache lines, how many cache blocks are touched by a piece of code, it will be a nightmare potentially. So it's important to actually virtualize the transaction. That's where the virtualization of the transactions becomes very important, because if the transactions are actually virtualized, the programmer doesn't need to worry about how big their transactions should be. If the transactions are actually smaller, you get better performance because you don't run into virtualization. For example, you don't run into issues where you need to context switch out and need to save the transaction state. Right? So it's still good, even when you have transactional memory, to reduce the size of your critical sections. It's a fundamental issue. Size of the critical sections, the smaller, the better, because handling large transactions are actually costly in terms of both performance as well as implementation complexity. Intel Haswell has an implementation of hardware transactional memory. Again, it has similar limitations for it to get good performance on code. Intel Haswell also has speculative lock elision as well. And AMD also has a paper on their extension for lock-free data structures and transactional memory. So this is my last slide on transactional memory. There are many research issues on transactional memory. This was a very hot topic a few years ago, with lots of papers being published in the architecture community. Now it's calmed down a little bit. It's being implemented in products, and it's not. It's clear that it's not a panacea to all parallel programming problems, although it could be a useful addition to the programmer's toolkit in designing better parallel programs. One issue is scalability. How do you actually scale conflict management and version management to a very large number of nodes? And I'll let you think about some of these questions. I'm not going to give you answers, but these are actually interesting research issues. The second is complexity. And complexity is mainly related to how to actually virtualize transactions without much complexity. How do you actually run long transactions and ensure that they execute correctly? In the presence of context switches and paging, how do you actually save transactional state? Especially if you have hardware transactional memory, how do you keep track of reads and write sets when you actually need to move the transactions to software if you have hybrid transactional memory? Handling I/O within transactions is interesting, and hardware complexity in dealing with all of this is interesting. Software transactional memory, pure software transactional memory, is unlikely to actually be very high performance enough to benefit a lot of programmers because there's a lot of overhead in managing transactions, read-write sets, aborts, commits, checkpoints purely in software. That leads to significant overhead, and people have tried to amortize and reduce that overhead with lots of optimizations at the software level and compiler level, but that overhead still seems to be very high. So hardware support for transactional memory is still needed, and once you start having hardware support for transactional memory, then the key question is how do you actually virtualize it? How do you keep that hardware complexity at check? Another issue is semantic sections. Basically, when you have atomic blocks that are nested with each other, what are the semantics related to that? I'm not going to talk about that, but this is more of a language and programming research topic. And finally, the key question, a big key question, is does transactional memory actually increase programmer productivity? Basically, the basic goal was to reduce the burden of the programmer in writing both correct programs and high-performance programs. And does this actually happen? And this is a difficult question to answer because there aren't huge chunks of programs that are actually converted to transactional memory. But a related key question is, does the programmer still need to optimize the transactions, optimize their sizes, and try to minimize the rate of conflict? And the answer is likely yes. But to what extent do they need to optimize as much as locks? It's less likely because locks have no latency tolerance. It's blocking synchronization. But this question is an open question, even though it's not a computer architecture class question where it's very hard to do a research project related to this. But I'd be very interested in listening to your opinions about what kind of potential projects you may want to do on transactional memory and speculative lock elision. So that brings us to the end of our lectures on speculation and parallel machines. We've covered a lot in speculation. We've talked about thread level speculation, and we've covered different approaches to parallelizing a single instruction stream, like dual core execution, for example. Slipstream processing was another example. And then we moved into using speculation to improve the performance of parallel programs. We talked about speculative lock elision. We talked about transactional memory. Remember the 4 concepts of speculative parallelization that still exist. For example, multiscalar is an example that shows those 4 concepts. And I'd encourage you to think about potentially different ways of actually using speculation to improve performance, as well as efficiency, as well as productivity in parallel machines. This is another fascinating area in computer architecture.